Alright, hell yeah. So this is the book Problems in General Physics. Now it's online, and hopefully I put the online version in the description. So this is the first problem, and someone's like, hey, can you do them all and post them, make a playlist? Well, this problem sucked, you know what I mean? Because it's relative velocity, and it's so hella confusing. So anyway, so what I did, I'm just going to go over maybe the 5-minute solution. Because we have a motorboat going downstream, and it's going faster than a raft. And the raft actually doesn't have a motor, it's just going at the speed of the river. And so the motorboat, though, is going faster. The motorboat does have some speed. And so the actual speed of the motorboat is the speed of the river, right? Plus the speed of the motorboat, you know what I mean? And then on the return trip, the speed of the motorboat is the speed of the river going this way plus the speed of the motorboat going that way. And in general, you know what I mean, maybe the boat can go upstream, but maybe it's just drifting this way. But, you know, using straight equations, where we're just going to say, well, the distance traveled by the boat downstream is going to be the velocity of the river plus the velocity of the boat. You know what I mean? Those things are additive. And we're doing that for an hour or 3,600 seconds. And then after an hour, we're going to switch directions. And now our speed is going to be the velocity of the river, but minus the velocity of the boat. And if the velocity of the boat is bigger than the velocity of the river, sure, then we're going back upstream. And then we're going to do that. I'm just going to say it's time remaining. I'm going to say we don't know that aspect. And then what we do is we do the same thing for the raft, because it wants to know, you go down and back, and then at the point where the raft actually hits 6,000 meters, you know, I'm doing everything in meters per second in this video. That's when you're going to try to find that time. So the time for the raft is like, well, the speed of the river times time, so that's going to be meters per second times seconds. Well, hell yeah, you're going to get distance. So you're going to have the velocity of the river for that hour. That raft's going to float for an hour. And then when you decide to turn back, you know, that time remaining, well, the raft's going to float for that time remaining. So this is going to equal 6,000. And we're saying that this also has to equal 6,000. So the continuity there is, you know what I mean? The total distance is the distance of the boat is equal to the distance of the raft is equal to 6,000 meters. You know what I mean? That's the problem statement. But the bizarre thing is you just have two equations. This is where I got stuck. This is why it took me 3 hours just to kind of come to a conclusion on this problem. Is because I don't know the velocity of the raft, and I don't know the velocity of the boat. And I don't know this time remaining. But these are good equations, because you're just like, well, you know what I mean? I don't know. You know, I know I'm going down for an hour, and then I turn back, and then at some point I'm going to run into the raft. I do not know what that time is. And so sometimes, and I didn't do this one in the problem, so this was brand new. Like, what if I just chose that if I went down for an hour and then came back for an hour and a half, you know, what would these distances be? So I did that. I said, well, I'm going to call this, for this hour, I'm going to call that T1 hour. And then on the return trip, I'm going to say, hey, this is T1 hour divided by 2. And then so when I FOIL these through, you know what I mean, I get this equation and then factor it. So I get this distance, if I did that, to be, you know, this 3/2 component plus this little extra. But if I do it just for this, for the raft, you know, it's for the time down to be 1/2. You know what I mean? Well, then I just have this component. But what the problem says is that these should be the same. The distance traveled by the boat should be the same as the distance traveled by the raft. They're not the same if your time is is half. The only way that they're the same, and I might have been able to get there from here, but the only way that there's the same is if this time remaining is equal to that 3,600 seconds, that 1 hour down. So that's the whole deal. Time down of 1 hour is the same as the time back for 1 hour for that boat. And I guess it looks like this. So the boat's going to do this, and then the raft is just going to float down the river. So this distance right there is 1 hour. But then fighting the current on the way back, this is what that 1 hour looks like. You know what I mean? And technically, it doesn't have to look like this, because the other way to look at it is like, well, hey, I'm going with the current, so I'm going real fast, but then now I'm just going slower. So that was 1 hour, but now I'm actually just going slower with the current, and this was another hour. You know, I'm powering back, but I'm still drifting downstream. This is the same thing as like, hey, if this drifted all the way to here, this is 2 hours. But there is the scenario where if the boat does have more velocity than the river, you know, it'll go down for an hour, but it has to fight the current. It's got to go back for an hour. But this right here is 2 hours. And I just find that fascinating. So I'm going to end this fast portion with a little diagram that I actually do in the full video. So we're gonna start the raft. This is the raft, and then this is the boat. So this is at 0, and we're just gonna say like I'm just gonna use different time frames. I'm gonna say, hey, in 1 hour, the raft is floating here. And the boat is going faster. In 1 hour, the boat went, you know, kind of twice as far. 2 hours, the raft is just floating down the river, but the boat is going twice as far. In 3 hours, the raft is floating down the river, the boat is over here, and we're just going to go to 4 hours, and then we're going to turn around. But now here, even here, this is the tricky question. When I turn around, am I going to be right here at 5 hours? No. So I have to go, in this case, the velocity of the river is like maybe just 1 meter per second. You know, we're going 1 meter per second. But the velocity of the boat, you know, maybe relative, I don't know what you actually call it, but it's actually the velocity of the river plus the velocity of the boat actual. And I say actual is like, as in if the boat was on a lake, that's how fast it would be going. And so we can see that this is equal to 1 meter per second plus, you know, another term. And we can see that we're going 2 here. So the velocity of the boat actual is 1 meter per second. But on the return trip, we're going to have the velocity of the boat relative, you know, on the return trip. That's going to be the velocity of the river minus the velocity of the boat. Well, that's going to be 1 meter per second minus 1 meter per second. So in this case, the river's going 1 meter per second. I am in a boat going 1 meter per second. Cool, I'm going 2 meters per second. But on the return trip, I'm going 1 meter per second against current that's going 1 meter per second. I'm standing still. So at time 5, I have not moved. But this, the raft is catching up. At time 6, the raft is doing 1 meter per second. I have not moved. At time 7, the raft is there, and I have not moved. And at time 8, finally, the raft passes me, or, you know, is like basically right next to me, and I pass the raft, or the raft passes me. The question basically says I pass the raft. And relative, sure, you're passing the raft, even though you're just not moving at all. So let's do this 1 or 2 more times, and then we'll start the actual video. But I think this diagram is bee's knees, and we'll do it 1 more time. And now we're going to say, or 2 more times. So now we're going to say that the boat is, and then here's the raft. The boat is going like, hey, this is 0, this is 1. But now the raft is just going, you know, floating down the river, 1, 2, but the boat's going 3. So this is 2 hours for the boat. This is 3 hours for the boat. This is 4 hours. So this is 4 hours for the raft. Okay, now we got to do the velocity of the river, or the raft is 1 meter per second. The velocity of the boat going this way is the velocity of the river plus, it looks like 2, plus the velocity of the boat actual. So that's 1 meter per second plus 2 meters per second. That's 3 meters per second going down. Now on the way back, velocity of the boat kind of relative is the velocity of the raft minus the velocity of the boat actual. So that's going to be 1 meter per second minus this 2 meters per second, and we're going to have negative 1 meter per second. So cool, on the return trip, we're actually going to be going upriver. So there's 5. All right, hell yeah. So there's the 5th hour's there, 5th hour's there, 6th hour's there, 6th hour's there, 7. It doesn't even look like we're actually going to meet, but hell, look at that, we meet. At the 8th hour, we meet right in the middle. So and then what are we taking from this? we're saying that, shoot, like I boated downstream for 4 hours. And then so I went that way for 4 hours. And then I went that way for 4 hours, and then the raft passed me. So cool, now we have, you know, this time in our problem, this time of 3,600 seconds going this way, you know, and we wanted to know what the time remaining was going that way. Well, it's just going to be equal to t is equal to 3,600 seconds. So that's the relationship. The relationship is that this time remaining is equal to the initial time that we went downstream, and that's going to be that 1 hour, or 3,600 seconds. All right, one more time, and then we can start the video. But yeah, the video is painful. The video is just like, well, because this problem sucked, because it really didn't have equations. Like, if you actually throw in this to be the same as that, like, the velocity of the boat falls out. It really does not matter what the velocity of the boat is, and that's what we're finding right here. So now we're going to have 0 for the raft, and then the boat at 0, and now we're gonna go 4 places for the boat. So the boat's gonna go in real fast. The raft is I'm sorry. This is time 1, and then here's the raft at time 1. Here's the raft at time 2, but here's the boat at time 2. So hour 2, hour 3, hour 4 for the boat. Hour 3, hour 4 for the raft. And again, so what do we have? Velocity of the boat is equal to the velocity of the river plus, well, it looks like 3 meters per second. And that's going this way. So then going this way, we have velocity of the boat is velocity of the river minus, what, 3 meters per second? And the velocity of the river is 1. So here we have, so we have 4 meters per second this way. And then we have 1 minus 3. This is negative 2 meters per second, or basically just 2 meters per second that direction. So on the return trip, we're going to be here at the hour 5, here at hour 5, here at hour 6, here at hour 6, here at hour 7, here at hour 7. And then, yeah, it's such a weird one. It doesn't seem like you're actually going to meet at that same time. But then there you go, hour 8 and hour 8. So if you travel down for 4 hours, you have to travel back for 4 hours to actually pass the raft. Now, so that's the continuity, and the continuity is that the time frame is the same. And then if you do that, and I don't have any more sheets of paper, but this distance then, you know, you can choose either one of these equations, and you can say that 6,000 meters is equal to the velocity of the raft times that 1 hour, or 3,600 seconds, plus the velocity of the raft for that second hour, which is 3,600 seconds. So now we can see that the velocity of the raft is just 6,000 divided by 7,200. Here, well, let's do it. 6,000 divided by 7,200, and we get the velocity of the river to be 0.833 meters per second. And so that's the answer. You know, find the flow velocity, but holy Toledo. You can watch the rest of the video of just the struggle, but I swear this one is because the equations are ghostly. You know what I mean? Like the velocity of the boat is irrelevant to the problem. And that is that's wicked. And the fact that the 1 hour down is the same as the 1 hour back, it's really it was really difficult for me to find that relationship. But I'm really proud of myself that I did this one without really, you know, looking for any answers, and just gutted through it. So this video, if you want to watch the long form, is just like, you know, how do you solve problems like this that don't have very specific equations or solutions? And this one sucked. It was like everything's just a little ghost, very wispy, and it was really hard to nail down exactly what was happening with it. So yeah, basically didn't throw in the towel on this one, and we came to a good representation. I have no idea what the actual, you know, how they solve it in books, but I'm just glad I did it my way, and there you go. So thanks for joining me, and if you wanted to watch the whole video, go for it. Alright, hell yeah. So we have this book called Problems in General Physics. Now, hopefully in the description I link the online. You know, you can find you can find the whole book online. So hopefully I'll buy it at some point. But anyway, a subscriber was like, hey, could you do every problem in that book? And you know what I mean? And I'm up for the challenge to at least do the first chapter. I love doing first chapters of textbooks because, hey, it's going to be fairly easy. And there's some fundamentals that carry through from the first chapter through the whole text. So anyway, I have not read this one. So that's pretty cool. Have not read this one, have not done this one. We got a motorboat going downstream. Cool. So maybe if it's going downstream, hell yeah. Maybe the flow is going downstream too. So it's going downstream, flow's going downstream. Okay, and then so there's a raft at some point, A. And then... Holy Toledo, I don't like these characters. But 60 minutes later... Okay, so sure. So at some point, what we calling that time zero? I have no idea. You know what I mean? We overcame. Does that mean we passed it? Passed a raft? 60 minutes later, we turned back. Oh, I apologize about my phone. 60 minutes later, we turned back, and after some time passed... the raft at a distance 6 kilometers from point A. Find the flow velocity, assuming the duty of the engine to be constant. Oh my god, you know what I mean? I think they could have done a better job of spelling it out. Well, let's do like a linear timeline. So we have time is equal to 0. Hell yeah, we pass the raft A. That raft is... Oh, and that's what they're saying. You know what I mean? It's hard. This problem is hard because they don't spell it out for you. The raft has no motor. Cool. So it is just drifting. So there's two ways to do these problems. One is just like, who cares about the river? Well, I don't know if you can do that. But anyway. So the raft is just drifting. So the raft is going to be a constant speed. Holy hell. 60 minutes later, so the motorboat, 60 minutes later turns back. And then after some time, like that time final, it passes the raft, but the raft is now 6 kilometers down. Okay, so my brain can't handle physics, so we just have to make this hella simple and say, you know what I mean? Let's say in 60 minutes you go down and back, and this whole thing took so this is the distance of 6 kilometers. In the motorboat you went down and back, and that took you 60 minutes. You know what I mean? 1 hour. And so that time took 1 hour, and guess what? The raft floated 6 kilometers downstream. So that means the flow of the current would be 6 kilometers per hour. So yeah, so this is a really good way to do it. Because now what we're saying is, it wasn't 60 minutes to go down and back and then meet the raft. No. It was 60 minutes to get to here. and then what? And then you come back to this point, you know what I mean? And you know what I mean? Because we have flow in this river. I'm sorry, I'm just not answering any of the problems that actually. But yeah, you have to get a feel for these things. You know what I mean? So if there was no flow in the river, and the raft just had a motor, you know what I mean? And you were faster. Where you went down and back, and then the raft is 6 kilometers away. I guess that's one way to look at it. Okay, all right. So now let's maybe solve the problem. So do we have a check on reality? We have a check on reality that the flow of the river has to be at least 6 kilometers an hour. No. Holy toledo, we got to figure this out. So let's go back to that example. This whole round trip, we're just going to say this whole round trip took 60 minutes. If that was the case, the flow of the river would be 6 kilometers an hour, because the raft drifts at 6 kilometers in 1 hour. Okay, but we're saying that took longer. So let's just say this took 2 hours, 2 hours for this thing to go down and then come back. We're just making something up. And then the raft drifts 6 kilometers. That means that the velocity of the raft would be 6 kilometers in 2 hours, or 3 kilometers per hour. And I think that's a low end. So now we have a low end and a high end, and the actual velocity of the river, the flow of the flow, is going to be somewhere between 3 and 6. I think I can live with that. And at the end of the day, cool, we could just say, who cares, and call it good. And I don't even know in miles per hour. Like, let's say it was 5 kilometers per hour. That's a 5K. I know that's a 5K in America. You run 3 miles. So that's going to be 3 miles an hour. Okay, so if I have 5 kilometers, that's 3 miles an hour. So this might be like 4 miles per hour. And this might be, what's 3 divided by 5? 0.6. So 6 times 0.6, is that how you do it? This is 3.6 miles per hour, and 3 times 0.6, this is 1.8 miles per hour. Okay, now we're just doing different problems. Yeah. Man, these problems suck. It's like the 2 trains going. So now we need to kind of figure out how to solve the problem. Okay, so what I'm gonna so here, we actually don't even need the raft. We do a river where you have like the 6 kilometer mark, and a speedboat travels down to that 6 kilometers, goes farther, and then comes back. And then and this is going to be 1 hour. And cool. So they're going to say the motorboat has some sort of speed. And I think we should convert all this to meters per second. I think that would be. Let's do that. So let's take a pause and do 3. Do factor label method. So we're going to do 3 kilometers in 1 hour. And then, we're going to throw 1 hour up here, and then we need an equivalence. Well, 3,600 seconds, hours cancel. Now we have kilometers per second. I'm going to throw 1 kilometer down here, and then that's going to be 1,000 meters. Kilometers cancel. Now we have meters per second. Hell yeah. And it was just 1,000 divided by 3,600. So we got times 6. And we got 1.66 meters per second. Check on reality times 2.25 is about 3.75 miles per hour, and then we thought it was 3.6, and whoops. All right, so cool. So we got that, and then the other end. We're going to do 3 kilometers per hour, and we're just going to do 3 times 1,000 divided by 3,600. Cool, and that's going to be 0.833 meters per second times 2.2. I think it's like 2.23 or 2.24, 2.35. But yeah, this is going to be about 1.8 miles per hour. And that's what we guessed. So hell yeah. So our guessing skills are pretty good. And we have 1.8 meters per second. So I want the velocity. Yeah, anytime you're doing problems, holy hell, get it in meters per second. That's going to be the first thing. I'm going to throw some more time on the clock. Alright, so now I'm just going to take a stab at it. I'm just going to kind of pick. Yeah, let's just pick something. So I'm going to say the velocity of the boat. Holy toledo. So the motorboat, it goes for 60 minutes and then turns back. You know what I mean? So, do we think? I mean, do we have any idea? Like I'm kind of bummed that I have no idea what the full time frame is, just from a guessing perspective, and that bums me out. Because if we have a motorboat that goes downstream for an hour, and then turns back, and after sometimes passes the raft at a distance of 6 kilometers from point A. Find the flow, assuming that the engine is just going at a steady pace. I mean, couldn't you do the problem where the motorboat actually is not going at all? You know what I mean? Sometimes I like to do that, just like, you know what I mean, try to throw a loop in it. So if the motorboat's drifting the same speed as the raft and they go for an hour, and then the motorboat just turns around, well, it met the raft, and they're at a distance of 6 kilometers per hour. So at what would be the flow of the river in that scenario? 6 kilometers per hour. Wouldn't that satisfy it? You know what I mean? I love finding loopholes. So a motorboat goes downstream, overcomes a... So, but that's the thing. It's like you have to have at least some sort of faster velocity. So you have something going on with the motorboat. 60 minutes later, it turns back, and after some time passes the raft. Oh wow. Okay. So anyway, so so the flow of the river has to be did we even get that right? I don't even think we actually got that right. You know that's no. I don't know what the hell I was doing right there. It's 0.833. Apologize. So meters per second. So if the flow of the river is going to be somewhere between 0.8 and 1.6, so like 1 to 1.5. It would stand that the motorboat the motorboat has to have a capability to go faster than the river. Because in the scenario, so this is interesting. Yeah, this is actually very fascinating. Because I just found one loophole, that if the motorboat has 0 velocity, then the motorboat and the raft are going to drift at the same time. And they're going to go for an hour. And then the motorboat's going to turn around, and guess what? The raft is right there, so technically the motorboat meets the raft. But no time passed in that. So that does not satisfy everything in the problem statement, but it's just fascinating. And so that would be a speed of the river of 6 kilometers in 1 hour. Cool. But we know that the motorboat has to have some sort of speed. So now the question is, so this is a cool question, because I've already determined, I think, that if the motorboat has a velocity of 0.5 meters per second, doesn't theoretically it will, oh no, it'll still meet the raft. Yeah, that's bizarre. Oh, okay. I thought I found a loophole where, if the raft was on shore, you know what I mean, and just stuck there, and then the motorboat was going downriver at 0.5 meters per second, but the actual flow of the river was 1 meter per second, and it went for an hour at 0.5 meters per second. That's kind of the bummer, because how many seconds is in an hour? We got 3,600 seconds, so we'd go 0.5 times 3,600. We went 1,800 meters. It's about a mile, 1,609 meters in a mile. But then if we did that, if we traveled at 0.5 meters per second for 1 hour, we would then we would go. We would be 1,800 meters. We would turn around, and then so this is going to be 6,000 meters. So our first check on reality is that no. What am I getting at? Okay, well, yeah, maybe there is something here. Like, I love slow rolling this one. I love, like, not knowing. These are crazy. You know what I mean? It's very good to make this like a 5-hour video. Okay, so yeah, let's stick. My mind just can't handle this. So we got let's say the motorboat's going 0.5 meters per second. It goes for a whole hour, which is 3,600 seconds. That's going to be 1,800 meters. Cool. So in 1 hour, it gets to 1,800 meters, and then starts to turn back. But the flow of the river is 1 meter per second. Oh. So right there, we're just theoretically wrong, because if the motorboat's going 0.5 and the flow of the river is 1, I mean, obviously we were going to get there. Like, it's like, don't think I was not going to get there. So anyway, so yeah, we have a velocity total of 1.5 meters per second going for 3,600 seconds. What is that, about 4,000, 5,000 meters? So 3,600 times 1.5. And we get 5,400 meters. You know what I mean? But even in our problem statement, no, this would work. This is fascinating. So now I'm interested in this problem because it says find the flow velocity. Yeah, I mean, I feel like this is like a really bizarre one where. Aren't we both going to be able to find the flow of the river, the velocity of the river, but then also the velocity of the boat? You know what I mean? Won't we have to know both? Okay, so we have the velocity total. So it only got 5,400 meters, and you might be like saying, well, how is it going to turn around and then meet the boat at 6,000 meters? Well, because it's not even going faster than the river. So the second it gets to here at 5,400 meters, now how far did the raft get in that 1 hour? Well, the raft got 0.5 times 3,600. So in this scenario, the raft gets, so we're going to say this is 5,400 meters. The raft, 1,000. We'll see what kind of fraction. We get a third. So the raft only gets a third of the way at 1,800 meters. You know what I mean? This might be the actual solution. You know what I mean? That's where just like guessing at least one number makes sense. And we're doing the scenario where the motorboat's actually going slower than the river. You know what I mean? Because I thought that would be a fascinating problem. You might just think that the motorboat is easily going faster than the river, but maybe the motorboat is actually just putting in over here and really can't go faster than the river, and so it's going to take out downstream. You know what I mean? So just the fact that it turns around at 5,400 meters. So now let's do the scenario where, hey, we have another 600 meters to float downstream, and we know we are. The second we turn around, we're only going 0.5 meters per second, but the river is going 1 meter per second. So, you know what I mean, using, summing vectors, you know what I mean, basically, well, what's the unit vector of velocity? Well, it's the sum of the vectors, and if we're just choosing the x direction, x positive, then it's the sum of the velocities in the x direction. You know what I mean? And that's going to give us a net sum. So we're going to go minus 0.5 plus 1. So we're going to get 0.5 meters per second in the positive x direction. Hell yeah. So, but we're only going to go for 600 meters. So now this is where I actually say, okay, what do we have? We have velocity. The units on velocity are meters per second. We have a distance of 600. That's going to be in meters. And so right now, what's the question I want to ask? I want to ask how long it's going to take to get there. You know what I mean? I already spent an hour boating downstream, and I got to there. But technically, this problem says I'm going to meet the boat at 6,000 meters. You know what I mean? That's when we're going to meet the boat. But that's only going to be 600 meters away, and I'm going at 0.5 meters per second. So all I'm saying is, like, hell yeah, the units help you get to the equation. You know what I mean? Because if I'm interested in time, well, time's downstairs. All right, we're back. Okay, so hell yeah. So time is downstairs. We got meters per second and meters. We want time upstairs. So it looks like we're going to have to divide by this. You know what I mean? So and we have to cancel out meters. You know what I mean? So that's cool. We want to cancel out meters. So I don't even know why I'm making this more complicated than it needs to be. But basically, we're going to go meters divided by meters per second. Hell yeah, meters cancel, and then time pops upstairs. So we're going to take that distance of 600 meters divided by, and I swear, like if you're new to like the factor label method, or being like, okay, I have velocity and I have time, if I have velocity and distance, how do I find time? Well, you can mess that up because you just mentally, you might not know if you multiply the two numbers or divide, and then if you divide, which ones do you divide by? There's two ways to divide numbers. There's only one way to multiply numbers. But okay, so we're going to have 600 meters divided by that 0.5 meters per second, and now could we do this one in our head? Looks like it's going to take 1200 seconds. But we'll do 600 divided by 0.5. That's the same thing as 600 times 2. Meters cancel, and we get 1200 seconds. And divided by 3,600. It is a third of an hour, and then multiply by 60. So we have 20 minutes. This might be the solution to the problem. You know what I mean? That'd be pretty cool. So cool. So now we're going to get down here in 20 minutes. So now we have a full time of 1 hour 20 minutes, which is also 3,600 plus 1,200. So we have 4,800 seconds to get down to here. Now the raft just had an initial velocity of the river, which, what did we say the river was? Well, the river is 1 meter per second. Maybe this will work. I have no idea. We're going to see how far we are off. So if the velocity of the river, or the velocity of the raft, is 1 meter per second, and it goes for 4,800 seconds, so you can just see that, hell yeah, this factor label method works, and we have meters on top, and we went 4,800 meters. Cool. So the raft, we did not. So we did what we were supposed to do. We went for an hour, turned around, and then boated back upstream. But we weren't boating upstream. We were still drifting downstream, but just at a slower pace. You know what I mean? So that was cool. Because I bet you this problem is a trick problem where, hell yeah, the boat is going slower than the river. Because now, what we're going to do is, and for the life of me, I don't understand why there's just one solution. You know what I mean? It seems like even if the river's going hella fast, and the boat should be able to go down and back with some sort of velocity to meet the raft at but maybe not. No, okay, that's a theoretical limit. Okay, cool. So I think from so yeah, we know that the problem probably is where the river is probably going to be faster than the boat. So now, is there a way to prove that the river can't be too fast? Yes, yeah. Obviously, the river can't be where in 1 hour the raft already gets to 600 meters. That was the initial check on reality. Man, I got to put triple stars on these, because that's how you got to start every problem, is your little checks on reality. Like, the speed of the river has to be between 0.8 and 1.6 meters per second. And honestly, this is just, like, we're assuming, this is a guess, but this is a hella high end. You know what I mean? This is the fastest the river can go. So in this scenario, the river can only go this speed. So I guess the better question is saying, well, let's say the river velocity of the river is 0.5 meters per second. Isn't there a velocity of the boat that would actually be able to do this? You know what I mean? Because if the river's going for 0.5 meters per second, and just in 1 hour, that's going to be 0.5 times 3,600. So in 1 hour, the raft's going to be at 1,800 meters. But then we're saying that the boat has to be way the hell downstream and then turn back around. So in this scenario, if the boat, this is a good one, because yeah, if the river's going hella slow, and in 1 hour the raft's only gonna go 1,800 meters, but it has to go 6,000 meters, so it has to go another 6,000 minus 1,800. So the raft's got to go another 4,200 meters in the time that it takes for the boat to turn around. And this time is set. It's set by the river. You know what I mean? So so if we have meters per second, we already know that's 4,200 divided by 0.5. We're gonna have 8,400 seconds, more than an hour, divided by 3,600. Where we're gonna have 2.3. We're gonna have 2 hours, 2 hours and 20 minutes. You know what I mean? So in that scenario, yeah, there might not be any velocity of the boat that actually satisfies that. Now, how could we actually just demonstrate that? That's all I want to do, is just kind of throw numbers on that scenario. To get close, like, what would be the velocity of the boat? Well, the velocity of the boat, oh, this is fascinating. So let's just pick some velocities of the boat. If in this scenario, if the river's going at 0.5 meters per second, yes, you have to have 2 hours and 20 minutes for that raft to go 6,000 meters. Isn't that what this is saying? If we have 6,000 divided by 0.5, divided by 3,600, that's going to be 3 hours. Oh, yeah, this is 2 hours extra. Holy Toledo. So, yeah, total of 3 hours and 20 minutes. But we're at least saying, yeah, it's going to be a total of 3 hours and 20 minutes for the raft just to drift 6,000 kilometers. Alright, hell yeah. So we're back, and I took about a 5-minute break. Now, I never wrote anything else down for this problem, but I did think about it for just a little bit. And we are going to solve this this one, you know what I mean? We really want to figure out what... but maybe... Oh, shoot. No. I'm still bummed out. Because what we want to do, I guess what I'm getting at is I'm trying to find a relationship here to actually, you know, make an equation. Because even right now, it's just like, it's not super obvious to me what an equation would be. So and maybe that's why this one is kind of difficult. So let's go back to this one where we have the river at 0.5 meters per second. And and what are we gonna say the velocity of the boat is? Or because that's the thing. Maybe we'll just assume that the velocity of the boat is well, didn't we say we were gonna assume it's like one? Did we already do that one? What did we? Well, here we said the velocity of the river was 1 meter per second. And then the velocity of the boat was 0.5. So now we're going to say the velocity of the river is 1.5 meters per second, and the velocity of the boat is 1 meter per second. So let's at least do that. and I don't know why problems. I think it's because you don't want to make mistakes. You know what I mean? And instead of just like saying, okay, what happens after 1 hour? Well, it looks like after 1 hour, I go 3,600 seconds. I go 3,600 meters in the boat. So that's what's going to happen after 1 hour. What's going to happen after 1 hour with the raft is going to go half that. It's going to go 1,800 meters after 1 hour. Okay. But now here's the interesting thing is that well, I guess we can solve it from two perspectives. Now, if the boat turns around, its average velocity is going to be 0.5 meters per second upstream. You know what I mean? So, and let's just say it just goes for another hour. You know what I mean? So then it's gonna go 3,600 meters downstream. So we're gonna go 3,600 minus 1,800 meters back upstream. So cool. Within another hour, it's gonna be where the raft was. But then the raft is gonna be at 3,600. So if that's the case, they're going to totally miss each other. And the boat's going to be back at 1,800. And the raft's going to be at 3,600. And then the problem says, is like, well, the raft needs to be at 6,000 meters. So obviously, it's going to take a hell of a lot more than 1 hour for that to happen. And the raft is never going to, when the raft gets... So yeah, let's do that, and that's what we did. We said that the raft after 1 hour is 1,800 meters. So 6,000 minus 1,800. The raft's got to go another 4,200 meters, and it can only do that in 0.5 meters per. That's the speed. And so we take this meters divided by this, divided by 0.5, and we see that's gonna take 8,400 seconds divided by 3,600, and that's that 2 hours 20 minutes. Okay, so if it goes for 8,400 seconds, it will be at 6,000 meters. So that's at the point after 1 hour. The raft got to 1,800 meters. The boat got to 3,600 meters, but then turned upstream. So if we're saying the boat is now going upstream at 0.5 meters per second for 8,400 seconds. See, that's the only thing I don't like about this problem is probably turning it into meters per second. Maybe that was a huge error, you know what I mean? Where I should have just turned it into kilometers per hour and kept it there, you know what I mean? But I'm okay with doing the meters per second. So we're gonna say that the boat is now going 8,400. I'm sorry, 0.5 meters per second. We need to find the meters. So yeah, we go 0.5 meters per second times seconds times 8,400. And now the boat went upstream 4,200 meters. It went downstream for that first hour 3,600. So we got 3,600 and then minus upstream 4. So by the time all that happens, by the time the raft actually gets to 6,000 meters, the boat is already way past the starting point, negative 600 meters. So that velocity of the boat sucked and didn't work. You know what I mean? So if the river is 0.5 meters per second, the velocity of the boat of 1 meter per second sucked, did not work. So now let's still say the river is 0.5 meters per second, and let's not get more sheets of paper because we just want to be able to do this mentally. So now we're going to say the velocity of the boat, hell yeah, it is 4 meters per second. I have no idea. Does this make the problem better? That's what we're going to find out. And so if now we know that the velocity downstream, velocity of the boat, you know what I mean, downstream, well that's going to be equal to the velocity of the river plus the velocity of the boat. Bummer. And I feel like, well, yeah, damn it. We have to go back because I made an error, you know what I mean? And that's what we do. We make a lot of errors. But if the velocity of the river is 0.5 meters per second and the velocity of the boat is, what did we say, is 1 meter per second? Yeah, then the velocity of the boat downstream is 1.5 meters per second. So it probably helps just a little bit. That means if you went for an hour, 1.5 times 3,600, the boat's gonna be at 5,400 meters. Now the raft is still 0.5 times 3,600. We've done that, and it still takes 8,400 seconds. But now this is where the boat is, and now it's going to turn upstream. And now the velocity of the boat upstream is going to be the river's going that way, and the boat can go that way 1 meter per second. So it's going to have an upstream of 0.5 meters per second. Cool, we just did that, and we got 0.5 times 8,400, and you got 4,200. So yeah, this was hella wrong, but I'm glad we caught our error. And we have 5,400 minus 4,200. But we're still just in no man's land where the raft is actually at 6,000 meters. So in this case, the boat got back up to 1,200 meters downstream, but the raft is at 6,000. So they're just worlds apart. Okay, so now we can do this scenario, and let's get the parameters right off the bat. So if the boat is going downstream, and it can go at a speed of 4 meters per second, and the river is 0.5 meters per second. So we have velocity downstream of the boat is 4.5 meters per second. It's going to do that for a whole hour. 4.5 times 3,600. Whoa, you know, we get 6,200 meters. Cool. The raft is still, after an hour, is just going with the flow. It's still going to be at 1,800 meters. It's still going to take 2 hours and 20 minutes for it to go the full 6 kilometers. And so we still have that time value. You know what I mean? So cool. We know where the hell the raft is. But now we want to know where the boat is, because the boat got way the hell down there. And now it's going to go 8,400 seconds times 0.5. Holy, we should have solved this right away. So if the boat goes downstream at 4.5, it's going to go upstream at 3.5 meters per second. You know what I mean? It's just the difference between the two. So holy Toledo. 8,400 times 3.5. I mean, we might be close. But no, it's just so much time that this thing is going upstream at 29,000. I mean, now if we increase the velocity of the boat, it's a losing game. So in this scenario where this is just the scenario where the velocity of the river. Alright, stepping back, this is the scenario where the velocity of the river is going to be less than the velocity of so it's like 0.5 or something. We know that the velocity of the river has a max. It cannot be 1.6. We already figured that. It has to be lower than that. And so we're doing the scenarios where the velocity of the boat is faster than the river. And in this scenario where the velocity of the boat is increasingly faster than the river, it sucks. There's just no way that's gonna work. Cool. But let's do this. Let's get the velocity of the boat to be like 0.75. You know what I mean? And so that's going to be really close to the velocity of the river, and then we're going to see. So the velocity of the boat downstream is going to be 0.75 plus 0.5. It's going to be 1.25. The velocity of the boat upstream is going to be 0.75 minus 0.5. It's going to be 0.25 meters per second upstream. Cool. So now the velocity of the river is the same. It's still gonna, if we go for an hour downstream, 1.25 times 3,600, we're gonna be at 4,500 meters. It's still gonna take that 8,400 seconds times 0.25. Now we're gonna go upstream at 200 meters. So this problem has a limit where you at least had to go downstream 6,000 meters. Because if you didn't go downstream 6,000 meters in 1 hour, well, how are you going to turn around? So that shows that the velocity if the velocity of the boat is greater than the velocity of the river, for the boat to even have a chance at getting close to that 6,000 meter mark, you actually have to at least go faster. In that 1 hour, you have to at least go 1.6 meters per second. Yeah, and I didn't even realize that. You know what I mean? So if we go 1.66 times times that 1 hour, 3,600. You know what I mean? You or 1.6. You know what I mean? Times 3,600. You do go 6,000 meters, but your velocity is faster than the river. So when you turn upstream, now you're actually losing ground because you can go faster than the river. And you're always gonna miss the raft. And we've just shown that if your velocity is hella, like even if your velocity is, in this scenario, was 2 meters per second, but maybe we can increase the velocity of the river. So yeah, maybe let's grab a new sheet of paper. No, let's keep this one. You know what I mean? We really don't want to write anymore. We just want to get an intuitive understanding. Until we start developing equations, we just want to do it this way. So we're going to do the scenario where the velocity of the boat is 2 meters per second. That's going to be the velocity of the boat of 2 meters per second. And then we're going to say the velocity of the river is like 1.5. Yeah. And I think this gets us closer to be like, well, if the velocity of the boat is 1.6, if the velocity of the boat is 1.6, and then the velocity of the river is also, oh no, you can't do that either. Man, yeah, this is an interesting one. I still am not finding the relationship where I can actually put an equation on this. But let's do it smart. So we got velocity of the boat is 2 meters per second. Velocity of the river is 1.5 meters per second. So now we have the velocity of the boat downstream is 3.5. And the velocity of the boat upstream is 0.5. So we're going to go 3.5 times 1 hour, that's 3,600 seconds, and we're going to go 12,600 meters. Now, the boat in that the raft in that 1 hour is going to go at a speed of 1.5 meters. So 1.5 times 3,600. So the raft is already at 5,400 meters, and you know, its difference is 6,000 minus that, and that's how many meters we have. We have a meters per second, a speed of 1.5. If we want to find the time value, we take that 600 divided by 1.5, and we get 400 seconds. So that's the turnaround time for the boat, but it's already hella down here, you know what I mean? So I just don't think it's ever going to get back. And then we have a velocity difference. Well, if we were 2 meters, if the velocity of the river is 1.5 and we're 2, we have a 3.5, but on the way back we just have a 0.5. So now we're going to be going 0.5 meters times 400, and we only go upstream another 200. So this goes from 12,600 to 12,400, and we're nowhere near that raft. Oh, this is a fascinating one. So yeah, it's so interesting playing around with an equation with two variables. So I think we've at least identified that. We have a variable that the velocity of the boat has to be something, and the velocity of the river, or the velocity of the raft has to be something. And obviously the velocity of the boat changes whether you're going upstream or downstream. But these are your two variables. So when it comes to solving equations, well, you need to have an equation. You need to have two equations, two unknowns. Man, this is going to be fascinating if I just talk into the camera for 5 hours and not solve this one. So now, knowing what I know, I'm going to grab a new sheet of paper, and what do I know? I think the boat has to be slower than the river. So that's the first scenario. And if the boat is slower than the river, so I have a time total, time t, and that's going to be in seconds. I know that, so one equation is the raft. The velocity of the raft is equal to the velocity of the river. And the units on that are meters per second. The total distance, L, so I guess we'll use L, is 6,000 meters. And the units on that are in meters. So the time total it takes for the raft to go 6,000 meters well, we have this unit of time, so we need to take these two things and get seconds. So seconds is downstairs, we need to get it upstairs, so we're going to do meters divided by meters per second. You know what I mean? And even this is the equation, you know what I mean? And this will give us seconds. So even right now we can say that, you know, this is time total, this is L, and this is the velocity of the raft. So we can go time total is equal to L divided by the velocity of the raft. Now that might seem so basic, but you're going to use that that kind of logic. Oh, excuse me. Had a lot of coffee this morning. You're going to use that type of logic, you know, to work with equations where you're just not super familiar, but you know the units have to match up. You know what I mean? So heck yeah. So now we have an equation for time final. That has to be the velocity of the river, and we're done. You know, we don't know anything more. So maybe we'll say that this is equation 1. We don't know the velocity of the raft, but at least we have one equation. Okay, so now I think we can actually go through the process of, now we're just going to say, hey, we don't know the velocity of the boat. So yeah, I didn't want to solve this from a purely equation standpoint, but I think we played around with this enough that we came to the conclusion that I think the velocity of the boat's got to be slower. So if I want to take a little tangent from writing these equations, I'll throw in a value for the river, and then we'll make the velocity of the boat just a little bit lower. Oh, and then we had to check on reality that this time total has to be greater. Time total has to be greater than 60 minutes. Has to be greater than 1 hour. And that was cool, because that was our first check on reality. You know what I mean? And it is so fascinating how that was like the easiest thing to see. But then once you kind of dive into the equations and the numbers, like, man, I don't even know why the hell that is. It's because the raft has to, whoa. It's the max speed of the river. Because we were saying, if the turnaround time of the boat is after 1 hour, but the raft already gets to 6,000 meters, well, the problem sucks, because when the boat turns around, the raft will have to be at 6,000 plus meters, and there's no solution to that. You know what I mean? The boat would have to instantaneously turn around and go, you know, infinite speed, but they're saying the speed has to be constant. So in that scenario, the top end for the river is 6 kilometers per hour, and we know that to be a top end of 1.6. So we know the velocity of the river has to be less than 1.66 meters per second. And that's cool, because the velocity of the river also has to be greater. Velocity of the river has to be greater than 0 meters per second. I mean, this really helps us out. I mean, 1 meter per second, again, 1.6 times 2.24 or whatever is 3.7 miles per hour. So 3.7 miles per hour. So this river is between 0 and 4 miles per hour. You know what I mean? So, and that's it. I mean, so literally you could do this where you could break 0 to 4 into chunks of, like, you know, 0, 1 mile per hour, 2, 3, and 4 miles per hour. And then obviously in this case 4 would be too high. But we can do that same 1.6. You could do like 0, 0.5, 1, and then 1.5. And then just hopefully, you know, 1.6 is just too high. And then you could figure that, well, you know 0 is not the case. So you have 3 scenarios that should be pretty close to what that should be. All right. So that's going to be the velocity of the river. Has to be between 0.5 and 1, you know, I don't know. I guess it could be hella slow too. All right. So yeah, well, let's take that tangent. So we have our equations. I want to throw in the idea that the velocity of the boat is going slower than the river. So we're going to go back to the scenario where the velocity of the river is 1 meter per second. I don't know. Yeah, maybe that's just. I mean, maybe that's pretty good. That's going to be the average between 0 and 1.3. 1 is pretty close. You know what I mean? So we're going to say just for velocity of the river is 1 meter per second, and the velocity of the boat is going to be less than that. And I guess we're just going to choose velocity of the boat is going to be. I don't know, 0.25 meters per second. So now the velocity of the boat downstream is going to be additive. It's going to be 1.25 meters per second. The velocity of the boat upstream is going to be takeawayative. It's going to be 0.75 meters per second. We're going to go for 1 hour. So if we do that, 1.25 times 3,600, we go 4,500 meters. Oh, we don't have a check on reality. You know what I mean? So the velocity of the... Oh, I never even thought of that. No, we do have a check on... That's why this scenario works. Because when we turn upstream, we don't actually physically travel upstream. Because the velocity of the boat is still less than the velocity of the river. We're still going downstream, we're just going downstream slower. So this was an error. You know what I mean? So obviously if the velocity of the boat is downstream at 0.25... the velocity of the boat upstream is not. It's not even going. So now we're just going to say the velocity of the boat on turnaround is downstream at 0.75 meters per second. I would rather do things like this than actually put negatives and positives that value up. So on turnaround, the velocity of the boat is still going downstream at 0.75 meters per second. Now, the velocity of the river is 1 meter per second, and you got to go for 6,000 meters. So there's a couple ways to do this. Is you can say that, hey, we're going to go for 1 hour anyway, which is 3,600 seconds. So we're going to have the velocity, because the velocity of the river is the velocity of the raft. So after 1 hour, the raft is going to go 3,600 meters. But we want to make sure the raft goes 6,000. So we're going to have 6,000 minus 3,600. Cool. How long is that going to take? Well, that's how many meters divided by the velocity. Remember that? Meters divided by meters per second pops up time. So we're going to have this 2,400 divided by 1, and you're going to have a time of 2,400 seconds. You know what I mean? Divided by 3,600, that's 40 minutes. But so you're going to have a time of 2,400 seconds. Now, the raft only got to here, but now it's going to be going downstream at 0.75 meters per second for 2,400 seconds. Now, in this case, seconds cancel and you get meters. So we're going to go 2,400 times 0.75, and you get an additional 1,800 meters. And this might be pretty damn close, because 4,500 plus 1,800. Hell yeah. So the boat is still downstream, but I'm so glad I did this. Because these problems, if you solve them from purely equation, I call that magic trickery. It's just like, who cares? You know what I mean? It's useful. It's very good algebra if you can do that. If you can actually, I think it all ties together with what the hell is the equation for B. You know what I mean? Down and back. And it seems like it's two equations. Like the second it turns around, it seems like you have to figure out how to actually explain that negative distance or positive distance in this case. Or that reduction in velocity. But at least the equation actually is a lot simpler, because we have proved that the boat, I think we've proved that the boat can't be faster than the river. If the boat's faster than this river, this problem sucks and it doesn't work. But cool, we're super close. So now the question is, well, do we slow down? Do we slow down or speed up? I think it comes down to this value. This value would be cool if it was lower. And how did we get this value? Well, we took 1 minus 0.25. So the velocity of the boat was too low. So if we said it was 0.3 meters per second, then this value would be lower, and we would have 0.7 times 2,400, and then we would have a lower value plus 4,500, and ooh, that's still not good enough. So but if it was 0.3 meters per second, then our velocity. So let's do that. So we're gonna say velocity of the boat is 3 meters. Velocity downstream is 1.3. Velocity upstream is 0.7 meters per second. So in 1 hour, we go 1.3 times 6,300. We go 46,800 meters. Hell yeah, I think we're getting close. We still have this, we still have, you know, the velocity of the raft is still we haven't changed the velocity of the river, haven't changed the velocity of the raft. It's still 6,000 minus 3,600 after that 1 hour, and this is how many seconds. So now we're going to go that many seconds times 0.7, and we get 1,680. So now we're going to go 1,680 plus 4,680. And we get 6,360 meters. Damn it, we're going the wrong direction. You know what I mean? So, oh, that's fascinating. I wasn't planning on that. But let's just keep going. I mean, that's the thing with problems. If you can't, I think for whatever reason your mind gets messed up. Just even throwing one value in there, it feels like you're gonna mess up. But even if you do, who cares? All right, hell yeah. So more time on the clock and we're back. And so yeah, now we're farther away from the boat. But you know, the graph might be like this. There might be like the perfect spot where we're like hitting on this side and then we're hitting on that side. But anyway, so let's try. Yeah, let's try just 0.4 meters per second. So now we're gonna have 1.4. We're gonna have 0.6, and so we're going to have 1.4 times that hour. We're going to be at 5,400 meters. Now we're going to be going downstream at 0.6 times that 2,400, and then plus that. Yeah, and then we're getting worse. So let's go to 0.2 meters per second. We're going to have 1.2. We're going to have 0.8. And we're going to have 1.2 times 3,600. So cool, we got 4,320 meters. And then upstream, we're going to go 0.8 times that 2,400. And we're going to have 1,920. Oh, hell yeah. Is this the right answer? Nope, we're still... So now the scenario is, holy hell, there might not be... Like, we're getting reduced, but this... See, that's why there's only one... We're understanding why there's only one value of the river and one value for the velocity of the boat. And the velocity of the river is still bound between 0 and 1.6. We're just choosing the velocity of the river to be 1 meter per second. But now, if we go down to 1 meter per second, it might not even help at all. So we're going to have 1.1 times 3,600. So we're going to have 3,960 meters. And now we're going to have 0.9 times 2,400, and we're going to have 2,160 meters. So add those two numbers up, and we get 6,120. So yeah, so I mean, now the velocity of the boat can just be 0. You know what I mean? But that is the limit on this. We've already identified that as a solution, which is absolute madness. So it's just fascinating that in this scenario, we're totally overshot. So for this velocity of the river, we are way overshot. So and we know it. You know, if we throw in velocity of 0, obviously, this is going to, we're going to go 3,600 meters, and then in 2,400 times times 1, and we're going to go 2,400 meters. So we're going to go 2,400 plus 3,600, and that's 6,000 meters. So we've already determined that if the velocity of the boat is 0, and the thing drifts down and then just turns around, after an hour, I mean, theoretically, the boat and the raft are just going downstream, and they're always together. So it doesn't matter orientation-wise what the boat does. You know, it can always just turn around and, oh, look at that, it's at the raft. But that's not the problem that they're asking. They want the velocity of the boat. That's the other thing. Velocity of the boat has to be greater than 0. You know what I mean? So do we choose a higher velocity for the river? Is that going to get us close? So let's do velocity of the river of 1.5 meters per second. And then the velocity of the boat, kind of that same thing. We're going to go 0.5. I mean, did we already do that one? But we're getting better at this. But now we changed the velocity of the river, which is the velocity of the raft. So now after 1 hour, we got 1.5 times 3,600. And that's why this high end kind of sucks too. But we'll try it. So basically, the raft after 1 hour goes 5,400 meters and can only go another 600 meters. That's why we've already done this one, 1.5. And that's only going to be a time of 400 seconds. So now we're going to say the velocity of the boat, well, let's get down to like just 0.1 meters per second and then see what happens. So now we're going to have the velocity of the boat downstream is 1.6, and on the way back it's going to be 1.4. So we're going to go 1.6 times 3,600. We're already going to be at 5,760. And then for 5,760 meters. And then for 40 seconds, we're going to be 1.4 meters per second. So 1.4 times 400. And we get 5,600. So we got 5,760 plus 560. No, we have to add those. Yeah, obviously it's going to be more than 6,000 meters. And in this case, the same scenario. If the velocity of the boat is higher, I just don't think this is going to be helpful at all. So maybe I made a bad assumption that said the velocity of the boat has to be less than the velocity of the river. Maybe in all scenarios where the velocity of the boat is less than the velocity of the river, there is no other maximum. I don't know. Let's keep playing around. So let's change this up, though. We're going to have 1.25 meters per second. And now we're going to change the velocity of the boat to be... how about just 0.25 meters per second? So now, so we have a downstream velocity of 1.5, an upstream velocity, well, it's still downstream, you know what I mean? Just on the return trip, it's just going to be 1 meter per second. At 1.25 meters, we're going to go 1.25 meters per second in an hour, and we're going to go 4,500 meters. 6,000 minus that is the remainder of the distance, and if we're going at 1.2 meters per second, we do this distance of 1,500 divided by our speed, and it's going to take an extra time of 1,200 seconds. So in this case, we're going to go 1.5 times 3,600, so we already went 5,400. And now we're going to go on a return trip, another 1 meter times that many seconds, 1,200. 5,400 plus 1,200. And then, yeah, so we're always overshooting it. So now I'm gonna say that probably, well, yeah, so we've already done this a bunch, and we're running into the same scenario where the only way this would work is if the velocity of the boat is 0. So now let's print off a new sheet of paper, let my camera cool, and we're going to do the scenarios where the velocity of the boat is bigger than the velocity of the river. But at least we still have these foundational principles that the velocity of the river still has to be between 0 and 1.6. Alright, hell yeah. Catch you on the flip side. Alright, hell yeah. So we're back, and I definitely took a little break, and I thought of a better way to... We might do some more guess and check. You know what I mean? We can always go back to guess and check. But I remember in one of the problems that you can solve these from kind of two different perspectives of like the relative speeds. So where you just kind of neglect the fact that the river is there, and we can even neglect the fact that the raft is there, because now we're just gonna say that we have and maybe it's better just to call it a car, you know what I mean? But we can still do a boat going down a river, and what we're gonna say is that after 1 hour, hey, we get to some sort of distance, and that required the velocity of the boat to have you know, some sort of downstream velocity. Now this is totally just the relative velocity of the boat. We're gonna say the velocity of the river is 0 for this. You know what I mean? This is, but in this case, the raft will never go downstream, but that's fine. What we're just going to say is that after the 1 hour turnaround, when we get back, we're just going to be at 6,000 meters. So we're going to have, this scenario is like, hey, in 1 hour, we're going to be past 6,000 meters, and then we're going to turn around and then go this direction. So we have two different times here. So we have, I don't know, I'm just going to say time 60 to get to the turnaround point. And then I'm going to say time remainder. You know what I mean? So I'm just going to make up my own little equation. I'm going to say time total is equal to time 60 plus time remainder, which is equal to 60 minutes, which is just that 3,600 seconds plus time remainder. So this is going to be my equation for time total, 3,600 seconds plus time remainder. You could also have another equation that says time remainder is equal to time total minus 3,600 seconds. Now, we don't know what time remainder is, and we don't know what time total is. But at least from this scenario, we can do the same thing. We can say that in 1 hour, we have to be past 6,000 meters. So we must, you know, this is 6 kilometers in 1 hour. So we must be faster. So the velocity of the boat, and now, right now, like we're doing, this isn't the actual velocity of the boat in the problem. This is where we're just, hey, we're just analyzing this is the velocity. You know how we chose, like in our problem, the velocity of the boat and the velocity of the raft, and the velocity of the raft was equal to the velocity of the river. So basically, we chose a velocity of the boat, we chose a velocity of the raft, and we said the velocity of the boat downstream was going to be the velocity of the boat, like actual, like on a flat lake, plus the velocity of the river. And then the velocity of the boat on the return journey was going to be the velocity of the boat actual, you know, on a lake, minus the velocity of the river, because it's opposing. And I guess I never wrote those two equations down, but you know, because I really wanted to go from the guess and check. But, you know, maybe for some problems, I don't know, maybe I just messed up my guess and check, you know what I mean, where I didn't really come to very good conclusions. I usually like to do that because, you can do like the mountain climber type Price is Right thing, like guess low, guess high, and then kind of figure out where the middle is maybe. Okay, but in this scenario, we're saying that this velocity is what we're assuming and calculating. You know what I mean? We're neglecting that side. Cool. So now in our problem, we're going to have the velocity of the boat has to be greater than 6 kilometers per 1 hour. And we've already determined that the velocity of the boat has to be greater than 1.66 meters per second. So in this problem, we said, hey, the velocity of the river is maybe like 1 meter per second, and then the velocity of the boat, you know, just by definition. Oh, and that's is that a true statement? I don't know if that's actually a true statement. Because holy, yeah, it is just messing with my mind too. Like what am I missing here? Because in this scenario, we're just taking relative velocity of the boat just on a flat lake, and you're saying you're going down, and then when you turn around, you're gonna have some sort of, so you have to have some sort of velocity. So you have to have some sort of velocity, and we know that we have to get past 6,000 meters, and then on the oh, that's fascinating. I hopefully that answers the problem. And then on your return trip, you go past 6,000 meters, and then your return trip you get to 6,000 meters. Yeah, but now I guess I just don't get what the problem is. Oh, I psyched myself out. This sucks. Let's see. Well, let's just throw some numbers at it. What do you think? Well, yeah, we know it has to be, yeah, so we're just going to choose 2. So let's choose the velocity of the boat is 2 meters per second. We're going to go for an hour. Yeah, sometimes too much thinking just is a mess. So we're going to go, in that 1 hour, we're going to go 7,200 meters. Now, when we do our turnaround trip, we're still going to go 2 meters per second. That's the part that's wigging me out. Because we know that's not true if the velocity of the river is something. So why is that? Why am I assuming that's the case? I have no idea. Is it because, yeah, we're just saying the velocity of the raft is 0? I don't know. Let's keep on with this. Holy hell! All right, so it's going to, yeah, we're going to go this many meters in that 1 hour, and then we have to go back the other direction. Oh, so I guess that's the difference. You know what I mean? We're still having this 2 meters per second, but this is in this direction. But now we're going to have velocity of 2 meters per second up, and we have to do the remainder distance of 1,200 meters, and we're going to do that in 2 meters per second, and so meters distance divided by velocity. That's going to give us the time divided by 2. And then we have 600 seconds. So now we have time remainder is 600 seconds. And then time total is going to be 3,600 seconds. Oof. 3,600 seconds plus 600 seconds. And we're going to get 4,800 seconds. And we want to know if that's even, yeah. And then from this, then you can deduce, well, if this was the case, how do we take this problem and then relate it to the actual problem? Well, we would have to say the velocity of the raft has to be, it has to travel 6,000 meters in 4,800 seconds. So there we go, 6,000 divided by 4,800, and now you have the velocity of the raft at 1.25, which sets up that the velocity, and this would be the velocity of the raft, and the velocity of the raft is equal to the velocity of the river because it just floats. Alright, so now we just want to see if this actually, see how far off we are. Because in our problem, so yeah, let's take this back to our original problem. So now we have the velocity of the boat. We said the velocity of the boat downstream had to be 2 meters per second. So that means, that's where I think I have something fundamentally going on with the way I set that up. But so cool, the velocity of the boat has to be 0.75 meters per second. And that's going to, so we're going to have a downstream velocity of 2 meters per second, and upstream velocity, oh, well, if this is the velocity of the boat, then the second parameter is still going to be downstream, and we're going to have 1.25 minus 0.75. And then we would have 0.5 meters per second still going downstream. So we're going to have 2 times 3,600. See, we're already past. So in this case, that just doesn't work. I don't know what the hell I was thinking. I'm sure I was onto something, but I guess I don't know how to set that up. You know what I mean? Or what the hell's going on with that. So let's just do more guess and check. Holy Toledo. So in this case, what did we have? We had the velocity of the raft, or the river, to be 1.25. And again, we said that the velocity between 0 and 1.66. This is the velocity of the river. Has to be, somewhere in between those two values. And then, yeah, so we have a check on reality there. Velocity of the boat is less. The velocity downstream is going to be additive. But we know that if the velocity is less, that's the crazy thing. If the velocity is less than the river, then on the way up it can't go upstream. So it's going to continue to drift downstream. So then we have a check on reality of this term. This term can't be greater than 1.66. So sure, the velocity of the river has to be less than 1.66. But the velocity of the river plus the velocity of the boat, if the velocity of the boat is less than the velocity of the river, this cannot be greater, has to be less than or equal to 1.66. Because on the return trip, you can't get upstream. And if you've already gone 1.66 meters per second times 3,600, you've already gone 6,000 meters. Cool. So from that scenario, what can we vary? We could make the velocity of the river bigger. But if we do that, yeah, so this is the check. If we... Oh, yeah. So, yeah, you just have to flip it the other way. And I thought we ran through all the scenarios where the velocity of the boat was less, but we still couldn't. The raft. The time that the raft took to get to 6,000 meters, the boat was already drifting farther. Alright, so I guess, yeah, we are definitely just going to go back to guess and check. And we're going to try the values where the boat is greater than the raft. Yeah, so let's say, the velocity of the river is 1.25 meters per second. Now the velocity of the boat is going to be 1.5 meters per second. So now the velocity downstream, so I'll just do this. Downstream is going to be additive, 2.75. Upstream, well, hell yeah, we are going to be able to go upstream by 0.25. So in 1 hour, we got 2.75 times 3,600. Yeah, we're just way too far. But let's go with it. So the velocity of the raft, 1.25 times 3,600 is 4,500. 6,000 minus that. And then let's get an equation for time. So see what we're doing here? We're saying if we chose the velocity of the river, then in 1 hour, we're going to go 1,000 or 1.25 meters per second times 3,600 seconds. And this is going to give us that initial distance after 1 hour. So this is going to be the distance 60. Cool. Perfect. And now what we want to know is we want to know distance total minus distance 60 is distance remainder for the raft. And that's going to be 6,000 meters minus distance 60. And then that's going to be the distance remainder. And now we still have the velocity of the river. So this is in meters. And then what we want to do is find that time remainder. And that's going to be, well, this distance remainder divided by the velocity remainder. Cool. So now we have an equation where we can throw this in. So we got dt minus d60 divided by the velocity of the river. So now just right now, at any point, we can find that time remaining. It's d total, which is 6,000, d60. Oh, and then d60 was the velocity of the river times time 60. So cool. So we got d60 is velocity of the river times time 60. And so we got time remainder is distance total. Yeah, and cool. Distance total is just 6,000 meters. Minus this, minus VR times 60 divided by the velocity of the river. So now, cool, because when you do this, now you can get equations where you can vary. That's the thing. That ultimately, you want to figure out how the hell this problem solved, and then get an equation so you can manipulate anything. You know, you can change this time to 120 and still get the same. Still get the parameters you're after. So let's do this. So we're going to have time remainder is 6,000 meters minus 1.25 times 60 seconds divided by 1.25. And this is in meters, meters per second, and meters per second. So seconds cancel. This is meters, meters cancel, time gets up top. So we get 6,000 minus 1.25 times 60 divided by 1.25. And we get a time remainder of 4,740 seconds. Let's do a check on reality, because that's the thing with equations is like, well, unless it's 100% perfect equation, you might have made a mistake. So in 1 hour, 1.25 times 3,600. Oh yeah, I already made a mistake because the time in seconds was 3,600. Holy hell. Yeah, so time 60 should be time 3,600. Yeah, because we're doing everything in seconds and meters, and I'm okay with that. So we have 6,000 minus 1.25 times 3,600 divided by 1.25. Yeah, let's get this equation. dt minus VR t 3,600 divided by VR. There's our equation for the time remainder of the raft after the raft goes for 1 hour. And this is a check on reality, because you the time total must be the time for 3,600 plus the time remainder. You know what I mean? The raft has to be floating down the river, and then in 1 hour cannot be at 6,000 meters. You know, it has to float another time remainder to get to that 6,000 meters. We at least know that aspect of the problem. Holy hell. Okay, so we're on a roll now. And what up? Let's see where we should go next. Well, I mean, that's why we just kicked this out. So we got 1.25 times 3,600. We're going to do a check on reality for this equation. We went 4,500 meters. We do 6,000 minus that, and we got to go another 1,500 meters, and we're going 1.25 meters per second. Meters divided by meters per second pops time upstairs, so don't mess that one up. And we got a time of 1,200 seconds. So that's going to be the time remainder. Now, is that what the hell we got? Sure. So we got 6,000 minus 1.25 times 3,600 divided by 1.25. Hell yes, this equation works, and we have the remainder time. Okay, so we're going to go downstream at 2.75, upstream at 0.25. This is the time remainder part. This is the time 3,600. So now the distance of the boat, I'm just going to call it dB. Distance of the boat is equal to and what's this velocity? You know what I mean? Because this is the downstream VB times T 3,600 plus, or I guess minus. You know, if we do have some sort of upstream velocity, then that's the velocity upstream times 3,600. Now let's worry about this negative sign, because you know, we might not be traveling upstream. So we're going to say the distance of the boat. What's the downstream velocity? It's just adding these two. So we're going to say is the velocity of the river plus the velocity of the boat. This is the velocity of the boat actual. You know what I mean? So I'm just going to put an A there, maybe. ACT. And yeah, velocity of the boat actual. Okay, and then the time is 3,600. Okay, now we're going to subtract that from the velocity, or how do we do this? Maybe you just add it, you know what I mean? So now we're going to say, but what we are going to do is we're going to do the velocity of the raft minus the velocity of the boat actual. And if the velocity of the boat actual is a bigger number, this is going to be upstream. And so I can just do an add here. And then we're going to have time remainder. Okay, hell yeah. And then booyah, I could throw that time remainder into there. And man, that was just a bummer. I didn't want to solve this with equations, but at least, but no, I mean, I have been using this strategy lately. Is just like, you know what I mean? Can you do a simpler problem? Can you even do the problem wrong? You know, or can you do the problem with a scenario that at least gets the boat past 6,000, but you at least know what you're multiplying together to actually get that value. And then can you put that into an equation? So let's just write that whole thing out, because maybe it'll spell itself out for us. So we have does that give us the distance? Sure, that gives us dB, and we're hoping that dB is going to be equal to dt, distance total of 6,000 meters. That's ultimately our check on reality that we want. But anyway, here we go. So we got velocity of the river plus velocity of the boat actual, T 3,600 plus velocity of the river minus the velocity of the boat actual times this. Cool, so now let's throw that in. We got the total distance, dt. Oh, sweet, we see dt pop up. Oh, sweet, so hell yeah. So we're going to have a dt right there and a dt right there. Booyah, I think that's going to be pretty cool. But But at least the cool thing about equations is as long as you don't mess them up, they're like 100% accurate. You know what I mean? And I find that fascinating. Okay, so T 3,600 divided by the velocity of the raft. Okay, hell yes. Now what the hell does this say? Obviously dt can't equal dB. And so what do we not know? Well, we don't know the velocity of the river, and we don't know the velocity of the boat. So that's where it's like we only have one equation, but we have two unknowns. You know what I mean? So, and I'm sure the other equation for relating, what's the relationship between the velocity of the boat actual and the velocity of the river? I'm sure it's something actually just really simple, but I don't know. And where did this check on reality come from? This was just like, hey, the distance the boat's traveling. So I guess the other check on reality is the distance the raft is traveling in this same amount of time. See how we have these time frames here? And I already messed up because this was time remainder. You know, obviously I guess I didn't mess up right here. But yeah, it's the downstream velocity of the boat, which is the velocity of the river plus the velocity of the boat. Actual, cool. And then this is a plus, you know what I mean, the return trip. And it's only going to be going upstream if the velocity of the boat is bigger. If this number is bigger, heck yeah, it's a negative number and you're going that direction. And then we're going to say on our timeline, this is positive x direction. You know what I mean? And this is 0 when we start out. Time is equal to 0. Raft and boat are in the same location. Okay, hell yeah. Now we're getting. And just from the fundamental understanding that what is this equation? This equation is the distance of the boat. Cool. So it goes down for an hour and then returns. Okay, so let's see if we can actually just get this. So we're going to find, hey, what's the distance of the raft? Well, the raft is, we can do the same equation. It's the velocity of the raft times T 3,600 plus the velocity of the raft times time remainder. Hell yeah. And we can see that, you know what I mean, obviously this factors out that it's just the velocity of the raft plus T 3,600 seconds plus time remainder. Cool. And I guess this video does have some continuity. You know, my goal is to push not the 5-hour mark, but hell, not even the 3-hour mark. But I think so in this last little bit, now we have continuity. And it all started with throwing numbers at it, you know what I mean? We throw numbers to find, you know what I mean, like why, and it just goes back to like, hey, if I have meters and I have meters per second, like how do I get time? Well, time's downstairs, so maybe I divide these two. Meters cancel, times pops upstairs. I mean, you just came up with an equation, you know what I mean? So that this would be like, hey, distance divided by velocity is time. Cool, you know, there's your equation. And then so that's why we throw numbers at things, and then we step back and be like, whoa, like didn't we just, anytime you add or multiply or divide numbers, like you're doing equations. And so then you can actually just, you know, write it out with the letters, values of what you're doing. And now we got it. And so now we have so here, yeah, d total, we're saying d total, sure, but here's a relationship. The distance of the boat has to equal the distance of the raft. Now we have 3 equations, you know what I mean? We have 1 equation, 2 equation, and 3 equations. Because this equation had distance of the boat. You know, in this one we said we only had 2 unknowns, but that's not, let's see. No, in this equation we knew, I mean, I guess this was, for this equation, you know, the way I have it written, this is our, you know, a 4th equation. Because, you know, let's say we don't know the distance of the boat, we don't know distance total. The other 2 are the velocity of the raft, velocity of the boat. But we do know that distance total and distance of the boat is 6,000 meters. Cool, check on reality there. So now in this equation, we only have those 2 unknowns. Velocity of the raft, velocity of the boat. Alright, hell yeah, took a little break, but we're back, and we were counting up these equations. We definitely have the two unknowns here. We have another equation that, what does this have in it? Well, it at least has the velocity of the river, and so, and it, yeah, so that's cool. Does that help us out? Well, yeah, because you could say that this equation could be solved for the velocity of the river has to be equal to the distance of the, we're saying distance of the river, which is just distance total, divided by the time total, which is t 3,600 plus time remainder. And then so you would throw that in. So yeah, that's kind of interesting. That the velocity of the river is real simple because we know that the velocity of the raft is equal to the velocity of the river, and the velocity of the raft has to be that total distance of 6,000 meters divided by the time total. And so that's what we have. The distance of the raft travel is just that distance total divided by time total. So now in both these scenarios we can change these to we can say all these are the same. Distance of the boat is equal to the distance of the raft is the distance total. But there you go. And man, I was still just kind of bummed that I didn't really want to solve this one with just equations. But what we're going to do is we're going to rewrite these. So we have the distance total. And then as we go over the equation, what you really want to do is have an understanding of what's going on. So we're saying what's this? Well, this is going to be the actual velocity of the boat, which is, like the relative velocity of the boat, which is the velocity of the river plus the velocity of the boat actual. Velocity of the boat actual is just what the boat would be if you turn the engine on to that setting. That would be the velocity around a river. Around a lake or whatever. Oh, mincing words. Okay, so we have that, and then it went for an hour, 3,600 seconds. That's going to be the distance it traveled for that hour. Now we're going to add it to, and again, this is adding to, but if the velocity of the boat is larger, then it's going to go back upstream. But if the velocity of the boat's not larger, it's going to continue to go downstream, and it's going to do that time remainder. That time remainder was that equation that we solved for, the distance total minus the velocity of the river time 3,600 divided by the velocity of the raft. And even right here, I have no idea why that is. So the time remainder is going to be... because don't we know that it has to be... why is it this? Well, let's go back and find out. So we said that the time remainder had to be... maybe we got this one wrong too. You never know. Because the time remainder is the distance total minus the distance that's... Yeah, it's the distance that you still have to make up. Oh yeah, we're doing the raft. We're saying that the raft after 1 hour gets to here, but it still has to get to that 6,000 meters. You know what I mean? So this is T 3,600, but we have a time remainder of the raft, but we do have a velocity. So we have a seconds, the time remainder. We have a meters per second, and we need to know and then obviously we know the distance down to here because that's going to be the velocity of the river in meters per second, and then you have the time, so that's the distance down to there. So we have the velocity of the river times T3, that's going to be the velocity down to there. We take in 6,000 minus that, that's going to be the remainder, 6,000 minus that. And then so this is going to be that remainder distance. And then so you're going to have meters, and then if you divide it by the speed of the river in meters per second, then you get time. So that's the time remainder. Okay, so that one you know, I could go over that one five more times just to make sure it definitely settles in. But hell yeah, we got it. Okay, so now we do, so there's one equation. I guess this is the other equation. We're just going to say the distance total, which is the distance of the raft. And you remember that one? You know what I mean? It's basically the velocity of the raft times that 1 hour. And let's do a check on reality there. You have meters per second times seconds. And yeah, you get meters. And so that's going to be the distance the boat travels after 1 hour. And the velocity of the raft is just the velocity of the river because the raft has no motor, it's just drifting with the river. So we have velocity of the river, time 3,600. And now it got to some distance, and we know that that distance has to be less than 6,000 because, you know, at 1 hour the boat got all the way down there and now it's turning around and the raft is still drifting to its final distance of 6,000 meters. Cool. So it's going to be the velocity of the raft times that time remainder. Hell yeah! And now we have two equations, and so, man, this is a bummer because now if we solve this one for velocity of the raft, we throw it into here, and maybe this is like the sad part. I feel like once you find out the solution, it's cool because then you know. And it's cool that you do it all yourself. And this one, hell yeah, I did it all myself. But it's just, a light bulb goes on. The second you actually know the answer, it's fascinating. You get the aha moment. And I'll think about this problem, even if I don't make more videos on this. I'll just be like, well, no duh. But I'm just disappointed that I have absolutely no idea if the velocity of the boat is going to be faster. So I still know that velocity of the river is between 0 and 1.6. You know, we definitely have that check on reality. But I just, for the life of me, I do not know if the velocity of the boat is less than or greater than the velocity of the river. And I wish, you know what I mean? I mean, should we really slow roll that? I mean, is that, because I already have this. I mean, if you want to do it right now, we just do, you solve for VR. So you go, and we'll do this in a few steps. Velocity of the river, and then you got time 3,600 plus time remainder. Oh, and maybe not. Maybe we actually have too many unknowns because we don't know the time remainder. And we're just solving for velocity of r, but oh, damn it. Yeah, so maybe we won't know. Yeah, we actually don't know the time remainder. Oh, damn it, I never even thought of that. Ah, bummer. So yeah, so maybe now I'm bummed out that I thought I was going to get to the end of the problem, and I realized that, no, we don't know the time remainder. Oh, but don't we know, I guess let's just start throwing stuff we do know. We do know that the total time is equal to the time 3,600 plus the time remainder. That does not help at all, because we still just don't know the total time. Oh, bummer. Yeah, what equations of these have... Oh, but we do know that the time remainder... Whoa, that's bizarre. Yeah, so let's throw that equation in. Yeah, I mean, just back to this equation, the time remainder. I'm glad I spent some time talking about it. And this is the deal with math, too. It's just like... Man, I kind of forget how we got this time remainder. Obviously, it was... the raft's going to float down a distance in an hour, and then we're going to subtract the 6,000, and that's going to get the remainder distance, divided by the speed of the river, which is the speed of the raft. That's going to be the time remainder. Whoa. Okay, so now we have it. So we can take... Oh, this seems brutal. I don't know why I'm making this so hellish. Yeah. Oh, so maybe. Oh, I still want to throw some more, numbers at this, just to get a feel. I just feel like that's a good strategy to have. I mean, if the velocity of the river can only be between 0 and 1.6, like, why shouldn't I be able to figure out what that is? All right, let's throw 10 minutes. You know, I got a 10-minute timer going. We're going to throw 10 minutes. We're going to come back to this page. But now we are going to just try to solve it with, we know the velocity of the river has to be 0, 1.6. We're just going to say the velocity of the river is 0.8. And then the velocity of the boat is 1. You know what I mean? Cool. Well, let's do it. So now we have, and I guess, and so we're going for an hour. So we're going to go 0.8 times 3,600. We're going to go 2,880. This is the boat, or the raft. And then we have 6,000 minus that. And you can see we're still using those equations we've already used. And so we're going to go meters divided by meters per second give us time. So we have this 3,120 divided by 0.8. And we're going to have a time of 3,900 seconds. So the boat is going to go downstream with 1.8. And then is it going to go upstream? Hell yeah, it's going to go upstream with 0.2. So we have 1.8 times 3,600. And we have 6,480 meters. And now we're going to subtract 0.2 times 3,900 seconds. And we're going to subtract 780. Oh, hell yeah. So for the very first time, so I'm so glad I did this, because for the very first time, our boat goes past 6,000 meters and then returns and maybe not for the first time. I forget. See, when you throw numbers at problems, you kind of forget if you overshot or undershot sometimes. But now we're going to have this 6,480 minus this 700, because we're going upstream that much. And booyah. So now we're there. So now we can kind of hone this. I'm going to go the velocity of the... And just for curiosity's sake, well, let's just make them equal. So we have 0.8 times 3,600. That one doesn't change. And then we have that remainder, so that time doesn't change. We have 0.8 times 3,600, so we got that far. And then on, oh, no. Hold, that's on the downstream trip, we're going 1.6. On the upstream trip, we ain't going anything. You know what I mean? So, so here we go. So we got 1.6 on the... And we're just staying in place. So this scenario says 1.6 times 3,600. Yeah, we went 5,600 meters, but now we're just staying in place. You know, cool. The boat's gonna reach 6,000, but we're just hovering in place. So that was a fascinating scenario. This one we overshot and then powering back. This one we undershot, but then just stayed there at the undershot. So yeah, in this one we stayed at the undershot. So now let's increase the boat speed. So we're going to go velocity of the river is 0.8. Velocity of the river is 0.8. Velocity of the boat is 1.2. Let's try that. So now we're going to have a downstream of 2 and an upstream of 0.4. All right, now we're on a roll. So we got 0.8 times 3,600. So the raft's going that far. It has to make up the distance. We can do that one again. And it's got a, you know, we've never changed the velocity of the river. So meters, it's got to go that many meters, and this meters per second. So divided by 0.8, and you get that time. Hell yeah. Now we're going to do, so we're going to go downstream. It's 2 times that hour, 3,600. So we're going to go hella, and then we're going to subtract 0.4 times 3,900. And we're going to subtract 1,560. So let's subtract those. And we get 5,640. Now, are we getting worse? It looks like we're getting worse in that scenario. This one we were kind of getting better just by staying put. So now we're going to now we're going to reduce. Let's reduce by 0.7. So velocity of the river never changes. The time doesn't change. Cool. But the velocity of the boat downstream is going to be 1.5. Upstream, it's not going to go upstream. It's going to continue to go downstream 0.1. All right, hell yeah. Now we're on a roll. 1.5 meters per second. 1.5 times 3,600. Hell yeah. And then we're going to add it to 0.1 times 3,900. And we get 5,790 meters. Now, are we improving? We're slightly improving. You know what I mean? So, how can we improve a little bit more. You know, we can always change the velocity of the river, but we're you know, because that's the thing. We might never be able to get to the 6,000 choosing this. You know what I mean? Because we think from the problem that there's only one solution for whatever reason. I don't know enough about math and equations to be like, oh yeah, there's only one solution. But maybe there's not. You know, we still haven't thrown in this into here and see if the velocity of the river is like a velocity of the river squared. We don't know. There might be a few solutions for this problem. And it probably is an x squared because we assumed that if the velocity of the river was equal to the velocity of the boat, like that satisfied the equation. So we think like, you know, hell yeah, that's satisfied, and then there's probably another satisfaction point. All right, so all right, we got 4 more minutes to experiment, and I might throw another 10 because this is going pretty well. So, should we just go to 0.6? I don't know if that's useful. So now we got a total of 0.8 plus 0.6. So now we have a total downstream of that, and then a total upstream. Oh, no, we messed up on that last one. No, we said we were still going down. Yeah, so we have a downstream of 1.4, and then still a downstream of 0.2. All right, 1.4 times 3,600 plus 0.2 times 3,900. Ooh, we're getting close. Cool, hell yeah. So let's really keep slowing this down. 0.5, and we got 1.3 meters per second, and then 0.3 downstream. Yeah, because obviously, well, let's do a quick check on reality. Because if this is 0, does that even help us? I mean, we're reducing that. That's what we're doing to this value. We're reducing it. So let's reduce it to 0, and then we'll have 0.8 downstream, and then 0.8 downstream. So we're going to have 0.8 times 3,600 plus 0.8 times 3,900, and we get 6,000. So yeah. So this scenario is the same, and we're chasing ghosts right now. You know what I mean? We're reducing this value to approach that value that we already know. If the velocity of the boat is 0, sure, you know what I mean. They're both going to drift to 6,000 no matter what, and then the boat will just turn around and be right next to the raft. Yep. So I think if I ever am coming up short on an initial guess, then we've just done a bad job. You know what I mean? So yeah, it just won't work. So let's do the velocity of the raft to be 1.2 meters per second, and then the velocity of the boat to be 1 meter per second. Do we still run into that same issue? So we got 1.2 times 3,600. And we got a distance of 3,420, 6,000 minus that, divided by 1.2, and we have a time of 1,400 seconds. So now we add these, we're going to go 2.2 meters per second. On the way back, we're still going to drift downstream 0.2 meters per second. But in this scenario, yeah, we already know this one's crap, because if we would have to have some sort of upstream. If this number is greater than 1.6, we've already overshot our 6,000 meters, so 2.2 times 3,600. And if we're still going downstream, that just ain't going to work. So this value would have to be at least 1.4. And then I think it just gets out of control, because we have 1.2 plus 1.4 times 3,600. We go 9,360. And then on the return trip, we're only going 0.2, and we're only doing that for 1,400 seconds. So we got 0.2 times 1,400, and we just go upstream 280. So yeah. So but let's go back to our velocity of the river as 0.8, and then the velocity of the boat as well. Didn't we get close with like 1? You know what I mean? Let's try that one again. Or like 1.2 meters per second. So in this case, we'll have that time. We're going to have a total downstream of 2, but now we will have an upstream of 0.4. So we go 2 times 3,600. Alright, I'm okay with throwing another 10 minutes at this, just throwing in numbers, you know, because I kind of want to get just good at that. So down for 2, up for 4, and if we have this 0.8, this is our time remainder, and so we're going to go 2 times 3,600, we're going to be at that, but now we're going to go minus 0.4 times 3,900. Yeah, and this is the scenario where, you know what I mean? We just need to reduce this velocity, and you can't reduce it enough, because if we do 0.8 times 3,600, or no, if you do 1.6 times 3,600, you just won't get there. So if this is 0.8, you just won't get there. So, but it's kind of cool. What I see right here is if the velocity of the raft and the velocity of the boat equal that 1.66, then if they're equal, so we're going to go 1.6 and then divide by 2. So if the velocity of the river is 0.83 and the velocity of the boat is 0.83, yeah, does this work? Holy Toledo, let's try it. So we have, how do I even store that in my calculator? I'm going to store it as x. So we have, and this is in meters per second. And so we're going to have x times 3,600. This is the distance. We're going to go 3,600 in 1 hour. And then 6,000 minus that is another 3,000 meters. We're going to divide that by x. Obviously, we get another 3,600 seconds. So I never even thought of that, you know, let's say the time down was 60 minutes and the time back, that would be weird, but I think we did find a solution. It's the fact that, okay, a motorboat going downstream overcame a raft at point A. That's just time 0, right? And then it goes for 60 minutes later and then turns back. And after some time's passed, the raft at a distance, after some time passed, are they saying passes the raft? I think that's a typo, or am I just reading this wrong? Then it turns back and at some time passes the raft at a distance. You know what I mean? It doesn't say that the boat has to be traveling upstream or down. We know relative velocities. The boat could be traveling downstream, but just slowly, and the raft passes it. Or the boat can be traveling upstream, and then the raft passes it. Or the boat has the same velocity of the river, and then the raft passes it. So, holy hell. So that's the scenario that we came across by using. So this is cool. I'm glad I spent that, because it's just like, what the hell is going on here with where you can't reduce one, but you can make them equal. So and then that's different. This scenario is different than the velocity of the river being 0. This scenario is different than the velocity of the boat is equal to 0 and the velocity of the raft is equal to 0, where they both just drift down to 6,000 meters. The boat just turns around and booyah, but the raft would never pass the boat in that scenario. Sure, they would be at 6,000 meters because they're both drifting the same speed, but how the problem says it, the raft will never pass the boat in that scenario. But in this scenario, it will. Cool. So we have, again, let's do it again. So we have x is this many meters per second times 3,600. The raft in that first hour went 3,000 meters. So now it's got a 6,000 minus that is the remainder distance, and it's still drifting downstream divided by x, and it's going to take another hour. Now the boat, on the other hand, is going that 1.66. It's going x plus x. It's going 0.83 plus 0.83, 0.866, and it's doing that for 1 hour, 3,600 seconds. And guess what number that is? So we have 2x times 3,600, and that, bingo, is 6,000 meters. Holy hell. So it'll be fascinating that after I throw these equations at this, that I just get, well, what the hell would I get? I would get that the velocity of the boat is equal to the velocity of the river, which is equal to 1.66. And then so maybe we do have an equation here where, like, this check on reality should have been an equation where the velocity, we know the velocity of the river. Oh, holy hell! Is this the actual? I don't know. You know, it's the weekend. You know what I mean? I just wanted to turn my brain off and see if I could do a problem for 4 hours. But yeah, no duh. If the raft isn't going, well, no. Well, we're saying time total. So in this case, whatever the time total is, that's in time in seconds. The velocity of the river is in meters per second. The distance is 6,000 meters. That's the distance the raft travels. So we know that the velocity of the river, or the, what do we know? Yeah, the velocity of the river is this distance divided by time total. So there's an equation. Velocity of the river is L. I'm saying this is distance total. I like how I say it's just distance total, and then we're gonna say that's time total, and there you go. And then we would do time total is equal to time 3,600, which is just 3,600 seconds plus time remainder, and then we could get an equation for time total because we have this equation for time remainder. So then we can get an equation for velocity remainder. And this might be, I mean, that's the same thing we did throughout. It was just fascinating that, yeah, this equation is this equation. Because if we rearrange this equation, we get dt is equal to velocity of the river times time total. But time total is that. So we get dt is equal to the velocity of the river t 3,600, the hour plus time remainder. Now this comes up a lot in equations where you're just like, oh, it looks like I have a new equation. Well, no, you already used that equation. You know what I mean? And so this doesn't give us any more useful information. But the light bulb went on. It was just like, oh, at the very beginning, I do know the speed of the river. And I should have, with equations, you know, it's good to just go there. You do know the speed of the river. It's just the total time for the problem, and then that raft to go there. You just don't know that time. That's the bummer. That time total is a variable you don't know. Now you can say that time total is the, you know, that 1 hour plus the time remainder. Sure, cool. Now you have an equation for time total, but you don't know time remainder. But then you can say time remainder, well, I do know that's the, you know, that 6,000 minus the hour that the raft goes with the velocity of the river. And then so sweet. So now I do know what time remainder is. But guess what? I don't know what the velocity of the river is. Damn it. So then you can say, well, maybe I know that the velocity that the boat is, or the distance that the boat is going, is going to be the velocity of the river plus the velocity of the actual boat for that hour, and then with this equation. So then I could be like, well, perfect. Yeah. So then I could actually solve. So if I was going in the same order logically with my words, then I could actually take this equation and solve for VR, even though it's everywhere. And even right now, I can see that VR times VR is VR squared. So that's one thing for analyzing equations. It's so good to be like, whoa, it's like, I didn't see that. Like right here, I just have one VR, but right here I have a VR squared. So to solve for VR, I would have to get it in terms of this. I would have to go A VR squared plus B VR plus C is equal to 0, and then use Pythagorean theorem to say that VR is negative B plus or minus the square root of B squared plus 4AC. and then all over 2a. And now if I throw in the a component, the b component, and the c component, sure, now I have an equation for velocity of r. And then I could throw it, and I could throw that equation for velocity of r. So I solve VR here. You know, I mean, I was just like, well, shoot, I don't know VR, but oh, I got an equation, and it has VR in it. So then I take that equation for VR and then throw it into here. But once I do that, what the hell's inside this equation? Well, this equation has something we don't know. We don't know the velocity of the boat. So once we do that, we throw this equation into there. We don't know, and this is cool because this just has VR. You know what I mean? This doesn't have time remainder. It doesn't have anything else. It just has VR. And we just solved the quadratic equation for VR. And then we can shove it back into here. So then we get this. But now we don't know, we still don't know time remainder. And we don't know velocity of the boat. So even through that explanation, it's just like, damn it. Do we still have one more thing that we don't know? So I'm going to take about 2 minutes to count these up. We know the distance total. We don't know the two velocities. We know that the hour, sure. We don't know the two velocities. So in this case, we just don't know the velocities. In this one, we don't know the velocity and the time remainder. Okay, cool. And then is this equation just rearranged that? I think that is, so that really doesn't help us, because this is, yeah, my bad. Like, even that, like, look at that. I thought these two were two unique equations. No, this is just rearranged. So, this is still two equations, and we have three unknowns. The two velocities, and then the time remainder. Damn it. And so then we still need to have another continuity. And maybe I'm back to, maybe I'm back to scratch. Oh, that is a bummer. And what? Huh. And this doesn't help, you know what I mean? This equation that says time total is equal to, you know, because then I would just shove it into here and great, then I don't know time total, you know what I mean? So that's a bummer. All right, so let's put that aside then, because we're trying to tackle this problem from two different perspectives, from the equation perspectives, and then can we just just guess and gut it out? So let's go back to that. So we have in this scenario we have 2x. This was the velocity downstream, and then upstream. So downstream we had 1.66, and then upstream we had 0. So we're going to go downstream for 3,600, and we go that 600 meters, and then when we turn around, we just wait. Oh, yeah. And then in this case, that time final, or that time total, is 3,600 times 2. It is 7,200 seconds. So that is a solution to this problem. And then let's actually, if that's what we found, let's. All right, hell yeah. So we're back, and damn it, you know what I mean? I don't even think I can solve this one. It feels like. I guess I just did though. You know what I mean? We found that both. Oh yeah. So we our camera cut out because it overheated. We were finding the flow velocity of the river. You know what I mean? So, but we did that. We said the velocity of the river is 0.833 meters per second, and it's just so fascinating that that's the only. Why is that? Why would that be the only speed of the river? Maybe we'll spend some time trying to prove that. Let me print out some more sheets. All right, so we're back. Got more time on the clock, and man, so the actual answer that one of the solutions was the velocity of the river is 0.83 meters per second, where the velocity of the boat is going to be 0.83 meters per second. That gives us, and then that's what we wanted to find out, was the velocity of the river. So now we're going to say, well, why? And we were really close with velocity of the river to be 0.9 meters per second. I'm sorry, the velocity of the river to be 0.8 meters per second. Now, I was already thinking in my head, we already kind of debunked this one. So why, if we change these just a little bit, why it changes our problem so much? So we're going to go 0.9 times that hour, and we're going to have a distance of 3,240 meters, and that 0.8 times this one's going to be 2,880 meters. And so the difference, 6,000 minus that one, and then with so that's going to be the remainder meter, but we have to go this fast, divided by 0.8. And so our time value is going to be 3,900 seconds. We remember that from before. This one's going to be new, 3,000. So the remainder distance is 2,760 meters, and but we have a speed of 0.9. So then our time value on this one's going to be 3,066.6 seconds. I'm going to store that as alpha t, and my calculator is t. And so now why can't, if we change this one a little bit, why can't we just change this a little bit and get the right answer? So now we're going to change the velocity of the boat to be, well, let's do 0.8 meters per second. So down 0.8 plus 0.9 is, so down we have 1.7, and then back up we're going to not have any. We're actually still going to be going down by 0.18. So we already know this one's toast because our overall velocity is greater than 1.66. You know what I mean? So if this velocity of the boat, the velocity of the boat plus the river is greater than 1.7, we already passed that 6,000 meter mark. And if we continue to go downstream, we will never go back to the 6,000 meter mark. Okay, so now let's change this to the velocity of the boat to be, so 0.9 plus 0.8, that's where we got too high. So this has to be 0.7. So this can't be any higher. No, it has to go the other direction. Yeah, so let's go velocity of the boat. If we do 0.9, well, obviously we went too far. So let's try that one. So we got 0.9 times 3,600. And now we're at 3,240. And then when we turn around, we're not moving. Whoa. I apologize. We got if we do 0.9, we got 0.9 plus 0.9. So the velocity downstream will be 1.8, and again we run into this scenario where we're past 6,000 and we have no velocity upstream. So we have to go velocity of 1. If we do that, then our velocity downstream is 1.9. So obviously we're passing the 6,000, but now we have a little bit up, and that's going to be 0.1 up. And so and we know that time frame is 3,066 seconds for this scenario. So we're going to have 1.9 times 36. So we're going to go 6,840, and then we're going to come back up 0.1 times alpha t. And we will never get back up there. So yeah, that's fascinating. So in this scenario, I think we've proven that we just won't, we'll just always be too far. So if our velocity is higher than the velocity of the river, we're just always going to be too far away. And then if our velocity is lower, we just won't approach 6,000 unless our velocity of the boat is 0. We can take that value all the way down to 0. So that was so we just did the scenario where the velocity of the river was higher than the actual velocity of the problem. And then I think we don't need to go over it again because we just did the 0.8 and we found the same scenario. You know what I mean? If our velocity is lower, I guess we can try one more. We can do this scenario where the velocity of the boat is 0.9. So our total velocity is 1.7. And so we're going to have 1.7 times an hour. And then we are going to go back upstream by 0.1 meter per second. So we're going to go minus 0.1 times 3,900. And so in that case we did pass. So yeah, it seems like shouldn't there be a solution here? So we went 5,730. So let's keep at this one. We're going to increase the velocity to 1, and we're going to have 1.8 times 36,000, and then we're going to have 0.2 meters per second. So minus 0.2 times 3,900. And yeah, we're getting worse on this one. So we really have to get the velocity of the boat to be not higher but lower. And the only way we can get the velocity of the boat lower, I mean, we can make them equal, and we can have 1.6 times 3,600, but then we won't be going upstream. And then if we make the velocity lower, like 0.7, so we have 0.8 plus 0.7. So yeah, we have 1.5 for that hour. And so we go 5,400, but now we're going slower. No, that's a good thing, because now instead of going upstream, we're going to continue downstream with 0.1. So we're going to go plus 0.1 times 3,900, and but in this scenario, we just won't approach 6,000. Like if we go even slower, if we go to 0.6, then we're only going 1.4, and then times that hour, and now we're really not getting there. And then the difference will be 0.2, so plus 0.2 times 3,900. And, oh, no, yeah, we do approach it. Yeah, so we actually approach 6,000, but you really have to take this velocity all the way to 0. So that's the other solution, but it doesn't satisfy the equation of the raft actually passing the boat. We're just saying that the boat and the raft travel at the same speed, and then so when they get to 6,000 meters, cool, the boat just turns around, but the raft will never pass it. The boat and the raft won't have any velocity in that case. Okay, so now I think we actually want to go back and solve this equation. And I thought we were home free, but I guess we weren't. We don't have enough equations and enough unknowns for whatever reason. I thought we did. I mean, hell. So I guess let's rewrite our equations. So this distance and do you want me to use distance total, or do you want me to use L for the problem? I kind of like this distance total. It's the only thing that actually makes sense to me. And so we're going to have, yeah, the relative velocity of the boat. That's going to be the velocity of the river plus the velocity of the boat actual. And then that's going to be I'm going to drop the velocity of the boat actual part. And then that's going to be for that hour plus, now on the return trip, we're going to have the velocity of the river minus the velocity of the boat for that time remaining. And we already have an equation for that. So we have dt minus vr for that hour divided by the velocity of the river. Okay, so that's an equation. Our other equation is... well, and then the other equation we already inserted, you know what I mean? So that's kind of a bummer too. Like we can't insert that one again. Yeah, that's not only was this an equation that used to have just TR in it, we already substituted that time remaining in there, and this equation still has two unknowns. So now now what we want to do is find a relationship. We need an equation for the velocity of the raft, proportional to the velocity of the boat. I'm surprised that I just don't have that equation. Yeah, because this is saying, this is essentially saying the velocity of the boat. So because we were saying that this was the distance the boat is going to be basically the velocity of the boat, which is the velocity of the river, plus the boat times that hour, plus the velocity of the river minus the velocity of the boat. This is going to be going back upstream, or if the velocity of the boat's lower, going downstream. Or if they're equal, you know what I mean? Hey, it's already going to be at 3,600, so that's what we were saying. But this is the time remaining. And then we have an equation, obviously, that the total time is equal to that hour plus the time remaining. And then we were going to say the distance that the raft actually goes is going to be the velocity of the raft times 3,600 times that hour plus the velocity, the distance the raft goes. And I'm using this R for like raft and river, but velocity of the river is equal to the velocity of the raft. I'm going to say dr is the distance the raft travels. You know what I mean? And so we have the distance the raft travels is the velocity of the river, because it's just drifting. And then for that hour plus the time remaining. Cool. But this is what we solved for here and then threw into there. That was useful. And then obviously we have that time total is equal to dr, the distance that the raft goes, plus the distance that the boat goes. That's equal to 6,000 meters. And the distance of the boat is the relative distance. So if we go in the positive x direction and then go back, we're subtracting that distance. And then we're just at a total distance of 6,000. Cool. So I don't know if I just need to take another break, because damn, this sucks. You know what I mean? This is the worst part of doing equations, and I'm just not satisfied that the velocity of the river and the velocity of the raft have to be the same for this problem. I don't know. That just doesn't satisfy me. I guess I don't know how that's useful to actually get my equations better. Or figure out what I'm missing. Oh, okay. So, this is interesting. No, I thought we already did this. I don't know why why you know what I mean? It's so, like, I think I'm overthinking it. Where, okay, this. No, am I overthinking it? Now these two equations are the same. So like obviously oh, this is weird. So all these are the same. So these are all equal to 6,000. And the way I have it written is these two equations are the same, and then I just solved this one for that time remaining, and that's going to be this distance r minus vrt at 3,600 divided by this velocity of the river. So so that's what we throw into here, and then we just get this equation. So that's all we did, is we just took these two equations and said, cool, those are going to be equal, and so we can just make them equal. But both of these equations have, they both have this time remaining factor in them. You know what I mean? So yeah, we can solve one for the time remaining, but we still have two unknowns. We still have we still just have two equations. No. We have three equations. We have two equations, but we have three unknowns. You know what I mean? So these are the only two equations. This equation and this and this equation are the only two equations, or you know, you could say that this is 1 prime, because all we do is have these two equations that are equal, and we have the velocity of the river, velocity of the boat, and this time remaining that we don't know. Holy hell! So this is where you have to find like a continuity, you know what I mean, that gives you a third equation, and I don't know why. I don't know if I just need to eat a sandwich. Man. And yeah, I'm actually, yeah, I'm gonna take a pause. Holy hell. Alright, hell yeah. So we're back, and we're on the home stretch, you know what I mean? I took about a 20-minute break, and, you know, we really wrote down what we knew, and I'm so glad with this problem that we actually started, you know, on the right track. The foreshadow that we're going to get to, you know what I mean, and here and there, is just realizing that if you paddle down for an hour, you have to paddle back for an hour, and that's got to be the trippiest thing, especially when you just don't see it. You know what I mean? When it's just not visually there. So that's the continuity. How we were saying, we were just like, well, we have 3 equations, but we have 2 equations. We have 2 equations: velocity of the raft, velocity of the boat, and this time remaining. And we just don't, you know what I mean? So at the end of the day, the time down, 3,600, has to equal the time back, time remaining. And so that's what we're going to go over. You know what I mean? But I'm proud of myself because I didn't look that up in a book. But honestly, I mean, you should probably look up, cheat on every single problem just to get a more well-rounded. But the only reason that you shouldn't do that is if you really want to, you know, just grind it out and find the patterns. You know what I mean? So that's what we did on this one. So and then this is the down and back, and you can do it, and we'll do that in a second. Okay, I got to get more time on the clock. All right, so brutal. Yeah, so we realized that if the velocity of the river and the raft floating in the river is at this max velocity of 1.66, after an hour, the raft is already going to be at 6,000 meters. But again, I really read this problem over because it said a motorboat going downstream overcomes a raft at this initial point A. That means, from the problem statement, that the velocity of the boat is greater than the velocity of the river. Whoa. Damn it. And again, the relative velocity. So I should say the velocity of the river plus the velocity of the boat. So this is the relative velocity of the boat. But those two in combination, I mean, all that really says is, heck, the velocity of the boat has to be something. You know what I mean? The motorboat is not just drifting. I guess that's all it says. But if the velocity of the river is, so in this scenario, where after an hour, if the raft is already at 6,000 meters, you know what I mean? The boat is farther than 6,000 meters because its relative velocity is the velocity of the river plus the velocity of the boat. And if it went for an hour, it's somewhere past 6,000 meters, and now it's got to turn around and we know from playing around with this, it doesn't have to be traveling upstream, but it just has to wait for either the raft to catch it, and the raft is surely going to be more than 6,000 meters. So this was the first check on reality, and I'm glad we did that. Now the other check on reality is that the river can't be 0 meters per second. The river can't be a lake. the problem still says, sure, if it's a lake, a boat passes a raft at this point. Cool, and it goes down for an hour and then turns around. But then at some point, the raft is going to be 6,000 meters downstream. Well, if there's no flow in the river, the time for that raft to go 6,000 meters is infinite. You know what I mean? So that's what I was trying to do. The whole issue is I didn't know what the heck the relationship was with this time remaining. Sure, we're going down. T1 is 3,600 seconds. I'm going to say time for an hour is equal to, time for 3,600 seconds. So yeah, we're going down, but then the time remaining is the time for the boat to come back to this 600 meter mark. And then, yeah, so what we did is, again, I just chose like, hey, let's choose 1.5 meters per second for the river. But what we found out that, if we do that, then the velocity of the boat can only be 0.66 to equal a total of the, and why is that? Because then if we have, let's see. It's because, oh man, I guess let's just do this one since we did it. If the velocity of the river is 1.5, we go for an hour and we go 5,400 meters. And that means that we only have 6,000 minus that. So we only have 600 meters remaining, but the raft is still flowing, so divided by 1.5. So we have 400 more seconds. And in this case, why do we know that the boat can only have a velocity of this? It's because let's say the boat has a velocity of 0.2 meters per second. Well, then the velocity of the boat initially is 1.5 plus 0.2, and then we're already at 1.7 times that hour, so we're already at 6,120. And our velocity of the boat's hella slow. So even after the hour, we're already at 6,120 meters. And then when we go to turn upstream, we're only going 0.2 meters per second. But the river is going 1.5 meters per second. So we're still actually going downstream at 1.3 meters per second. So there's no time in the universe to ever get back to a location that's 6,000 meters. So this shows that that this cumulative value of the velocity of the river plus the velocity of the boat, if the velocity of the boat is less than the velocity of the river, right? But adding those two together, we know that velocity of the boat plus velocity of the river has to be less than or equal to 1.66. Because if these two cases happen, after that hour, you're already going to be past 6,000 meters, and you're not going to have, and your velocity of the boat is less than the velocity of the river, so you ain't going upstream anymore. So it's physically impossible to get to that 6,000 meters. Hell yeah. So at least we've done this problem enough where we can actually talk through the scenarios, fluently, so we're not stumbling on that. But there is this scenario where, it has to be less than 1.6. How about if it's equal to 1.6? So that's what we did here. And then we still come up, in this scenario, it shows, hey, if they're equal, and then we're going to add them together, we're going to have, this is our velocity times 3,600. So booyah, we're at 6,000 meters. But now when we go to turn upstream, well, damn it, we're not going upstream. We're still drifting that way. And did the raft meet us? No, because the raft had a velocity of 1.5 times 3,000. So the raft is only at 5,400 meters. We're already at 6,000 in this case, and we're still drifting downstream. We will never pass the raft, And so it's a bummer. Now, we're drifting downstream less than the raft. The raft's going this speed, we're going this speed downstream. So technically, if we face upriver, because we're powering upriver, we will pass the raft. You know what I mean? we're all going downstream, but the raft is passing us, and we're gonna pretend like we're passing the raft. So that's the scenario that happens. Okay, so from that, it was from this that I kind of had that like aha moment, and I don't even know how to get there in here, but I do know we're gonna end on a strong note and finish it with this, because we can do this once, twice, 3 or 4 times, but really hone in the fact that if we go down for an hour and we're in a river that has flow, and then you have something that just floats in that river, you know what I mean? The time it takes to go this way and that way will be the same. And I don't even know how to explain what the hell I was doing right there, so let's just go right to here. So what I did is I started with, get some more time going. Alright, so what I did is I just said, hey, this is going to be the river. The river is just going to kind of go at a constant speed. And so at time 0, here's the boat at 0. Now we're going to say the boat is right there at time 1, and then the river is right there. So no, this is the raft. I'm sorry. This is the raft, and this is the boat. So at time 1, the raft's right there just floating with the river. But the boat is going faster. So here's time 2, time 3, time 4, perfect. And this is for the raft 1, 2, 3, 4. Now at let's say 4 seconds, the boat is going to turn around. So now where is the boat going to be? Well, that's why we need to come over here with the equation. We know that the velocity of the river looks like it's 1. Well, what's the velocity of the boat? You know what I mean? Is the velocity of the boat 2? No. So this is where this problem is just way different than, like, you know what I mean? Because I was confusing it. I think everyone's going to confuse it just with like 2 cars like racing each other. Hey, let's say you have a Sunday driver going 30 miles an hour and they're doing this. You know what I mean? But then you have somebody going 60 miles per hour and they're doing this. So you have 0, 1, 2, 3, and 4. And then 0, 1, 2, 3, 4. Maybe these are like hours of driving. And then on the return trip, you know what I mean? This one's going to go 5, 6, and then we're going to see where they meet. So we're going to go 5, and then, so if it's a problem like this, at hour 5, this car is going to be right there. This car is going to be right there. And then we could say that they're going to meet, like this one's going really fast. So let's just say 5.5 hours. You know what I mean? You wouldn't be too wrong on that. You wouldn't be too wrong on that. So in this scenario, at time 4, this fast car is going to turn around and go back the other direction. And look at this. It went for 4. Both cars went for 4 hours. And then on the return trip, this fast car theoretically caught this one in an hour and a half of going the other direction. Okay. So I think that's where common sense, that's where most people's minds are. You know what I mean? But when you have something in a river floating down, let's look at this. So the velocity of the boat is not 2. The velocity of the boat is the velocity of the river plus the velocity of the boat actual. You know, the velocity of the boat on a lake. So we're going to say velocity of the boat actual is equal to the velocity of boat on a lake. And that's going to be the, you know, and I think you would just say it's the relative velocity of the boat. So we're going to say velocity of the boat relative, maybe. But I'm just going to say it's the velocity of the boat. There you go. And so that's going to equal 1. Because now, I'm sorry, that's going to equal the velocity of the river, which is 1, plus the velocity of the boat. We're going to say the velocity of the boat's 1. So that's going to equal 2, and that's exactly what we did in this picture. The boat moves 2. You know what I mean? And then the raft moves 1. And then so on the return trip, the velocity of the boat is the velocity of the river minus the velocity of the boat actual. So the river's going that way at 1, but the velocity of the boat is going upriver by 1. You know what I mean? So 1 minus 1 is 0. So this just stays put. So the raft still goes. So at 5 seconds, the raft's there. At 5 seconds, this point didn't move. You know what I mean? And so that's where this diagram, if you're looking up there, of what I was doing. So then at time 6, the raft is right there. But we haven't moved. You know what I mean? Well, our velocity, we're going upstream. We're powering upstream by a speed of 1, but the river is a speed of 1. 1 meter per second up river is our speed. The river's going 1 meter per second. We're just in place. So at time 7, we're still right there. And at time 8, we're still right there. Booyah! So theoretically, from that Einsteinian view, you know what I mean? Hey, we're now passing the raft. You know what I mean? The raft's going this way. We just passed it at time is equal to 8. So if we go back to this scenario, is like, whoa, we went 4 hours this way and then returned and it took an hour and a half. Same thing here. If we say these are hours, boat goes 4 hours downstream, returns, and it takes to hour 8 or just another 4 hours. So that's the whole relationship, that this time remaining is equal to the time that you went out. You know, that time of 1 hour, 60 minutes, is going to be the same 60 minutes to actually pass the raft. And it's just interesting. So we're going to do the second scenario where at time 0, now the boat is going to be going this speed, 1, 2, 3, 4. So at one time of 1, you know, whatever, the raft's going to be there at 2, at 3, at 4. And now let's see what so we got the velocity of the river is 1, velocity of the boat is equal to the velocity of the river plus the velocity of the boat actual, and that's going to be 1 plus 2 it looks like, and that's going to be 3, so we got 3 increments here. Cool. On the return trip, the velocity of the boat, and I'm going to be like, hey, downriver, and the velocity of the boat upriver is going to be the velocity of the river minus the velocity of the boat. So that's going to be 1 minus 2 is -1. And so and then just by the arrow, that's going to be, you know, one unit that direction. So at time 5, we're going to be right here, and at time 5, we're going to be right there. At time 6, we're going to be right there. At time 6, we're going to be right there. At time 7, we're going to be right there. At time 7, we're going to be right there. For a second there, I thought this wasn't going to work. But hell yeah, at time 8, we're going to be right there, and then the raft's going to be right there. I'm going to do this one more time, you know, with 4. So we're going to, just to make sure, you know, I mean, this is, modeling is the most important thing about math and sciences. And let's do this like this. So we're going to go, the raft is right here, the boat's right there. At second 1, the boat's right there, the raft is right there. At second 2, the boat is right there, the raft is right there. Second 3, there we go. And at second 4, the boat is right there, the raft is floating down right there. And so now we need to figure out, we know what the velocity of the river is, looks like it's 1, but the velocity of the boat is the relative velocity of the boat. You know what I mean? It's and it's going to be the velocity of the river plus the velocity of the boat actual. And again, the velocity of the boat actual is like, hey, whatever the speed of the boat would have been just on a lake. And that's going to be, it looks like 1 plus 3. 1 plus 3. So then that's going to be that direction. And then so now on the return trip, we're going to have velocity of the boat is velocity of the river minus the velocity of the boat actual, which is 1 minus 3 is -2. Cool. So or is going to be 2 units that way. So return trip, and then this trip is going to be 4. 4 that way, 2 returning. So is that what we see? We're going to go 4 that way. And then, okay, let's return. So we have 5, 5. At time 6, 6. And these could be hours. At time 7 hours, there you go, 7 hours. And then at time 8 hours, you're going to be right here. And then the raft's going to be right there. Holy hell. But for whatever reason, like this problem killed me because I was trying to solve it from the idea that, you know, you find equations, you find unknowns. But man, this relationship seemed to be super hidden, you know what I mean? And then I knew I needed like a relationship between, like anytime that you get 3 equations and only have no. Anytime you have two equations and then only and have three unknowns in those equations, you need more things to relate the problem. It's called continuity, you know what I mean? And so here is the continuity between the time down of 60 minutes and then the time remaining. That's also going to be 60 minutes. Or t of 3,600 seconds is going to be equal to time remaining. So now, let's slow roll this out with confidence and go back through our equations. And I think I'm going to post the solution at the beginning, because this was the most, first chapter, first problem. There's a lot of these in physics. I mean, this could discourage you this could scar you for life, you know what I mean? Especially if you're just like, nah, I don't get it. And so if I don't get the first problem in the first chapter, why would you be able to get any of the others? Alright, hell yeah. So let's solve this thing for real now that we know all the equations to use. Let's see. So we're going to say maybe first that the total distance, and let's use the variables too. So the total distance L of 6,000 is going to be the velocity of the river, and let's get our units, because if we have meters and then we have meters per second and we want these to equal, well, we got to multiply by seconds. I don't know, I love doing this for the units or the equation, you know what I mean? It just works out so much easier. So now we have to multiply by the time. So the velocity of the river, and then we're basically saying that time total. Time total is the time down for that 1 hour or 3,600 seconds plus the time remaining, you know what I mean, the time back. So and so we're going to have those two values. We're going to have t 3,600 plus the time remaining. Okay, so that's going to equal to 6,000. Now for the boat, though, we're going to say, hey, that distance for the boat is going to be the velocity of the boat. You know what I mean? So, and I guess over here we're going to say the velocity of the boat actual is the velocity of the boat on a lake. Okay. And then so we're going to say the velocity of the boat is equal to the velocity of the river plus the velocity of the boat actual, and this is going to be going downriver, and then going upriver, the velocity of the boat is going to be velocity of the river minus the velocity of the boat actual. So we kind of have those two relationships. So we're gonna have so downriver we're gonna have the velocity of the raft plus the velocity of the boat. And I guess I'll put actual, you know what I mean? And that's going to be on the way down, we're going to have that time of 3,600 seconds. Now on the return trip, we're going to have plus, but we're going to have velocity of the raft minus the velocity of the boat actual, and that's going to be that time remaining. And this is where we got those two equations, but we didn't know the velocity of the raft, we didn't know the velocity of the boat, and we didn't know the time remaining part. But through that analysis, we know that the time remaining has to be equal to t 3,600, so is time going down for that hour. So if we know that, this just gets real easy, because now this first equation goes L is equal to, it's just going to be 2 times. So we're going to have VR, but then we're going to have 2 of these. So I'm just going to go 2 times time 3,600, and basically we know this is 3,600 seconds, or just 1 hour. So that's that equation, and I'm going to say, hey, this is 1, this is 2, and then this is 3. And then so I'm just going to say this is 1 prime because we did something different to equation 1. Now we're going to do something different to equation 2. So 2 prime is, hey, we're going to throw in this value of that time remaining, now that we know that continuity, you know what I mean, hell yeah. So this is going to be VR plus VB actual time 3,600. plus velocity of the river minus the actual velocity of the boat times t of 3,600. Cool. And now we can sure simplify this. Holy Toledo, this is going to be... and then the other thing that I might do is just, hey, t 3,600, that's a pain in the butt to write, so I'm just going to, that's t 1 hour, you know what I mean? So we're going to say velocity of the river, t 1 hour, plus velocity of the boat, and it'll be easier if I can just drop this velocity actual. Like, we get it that this is the velocity of the boat relative, you know what I mean? These are the relative velocities of the boat. All right. Yeah, these are the relative velocities of the boat if you were on shore. If you were on shore, you would see this boat going really slow upstream, you know what I mean, maybe. Or maybe just still drifting downstream, you know what I mean. But the actual velocity of the boat is still the velocity of the boat on a lake, you know what I mean. Okay, so yeah, we were right on that relative velocity term. Anyway, so we have the velocity of the boat, T1, plus velocity of the river, T1, minus the velocity of the boat, T1. Cool, so the velocity of the boat just pops out of here, and now we have that the length of 6,000 is just equal to... It's the same darn equation, so this was really disappointing. The fact that this is the continuity, it makes something that seems complex very, very easy and very straightforward. Because even when we were saying, oh, we initially we were like, hey, let's solve this one for the time remaining, and then shove it into here. Well, then that's going to be a function of the velocity, and then you're going to have a function of the velocity squared. But this continuity just makes the whole thing, just the whole problem, just like, well, the simplest thing. So this whole problem came down to that continuity. And if you didn't see that, you're going to quit physics. You know what I mean? But yeah, so this is the caveat that's very fascinating. I must have a short-term memory, because not just, it could have been just 1 week ago, maybe 2 weeks ago, and I was flipping through my physics book, and I ran across a problem like this that, basically said, yeah, if you go one direction, it's gonna, in that time, well, you have to go the other direction in that time. It was a problem basically just like this, but that was the continuity. But how are you actually going to figure that out? I think we figured that out doing the actual process of how you figure things out. You know what I mean? You just throw numbers at them and be like, well, and then you can do the equations unknowns and realize, no, I still have still got 2 equations, 3 unknowns. I don't know what the continuity is. But we did it, you know what I mean? So I'm pretty proud of myself that I actually stuck with this one. And cool, and so you get this same relationship, you know what I mean? Like, so times T1. So there you go. You get the same relationship down here with this 2 prime as you did there, and then so we have the velocity of the river. It is just it's just it's hella simple. It's just L2 T1. You know what I mean? Velocity of the river is just L divided by 2t, and that's going to be 6,000 meters divided by 2 times 3,600 seconds. And that's all they wanted to know. And that's 6,000 divided by 2 divided by 3,600, and you get 0.833 meters per second. You know what I mean? 0.833 meters per second. Probably 3 decimal places, even though that's ridiculous for this problem to have 3 decimal places. And we did it. And then if you go back and be like, well, what was the actual velocity of the boat? I kind of wanted to know that. Well, you can go back to any of these equations that had the velocity. But this one sucked because it got rid of the velocity of the boat. So how is that? Is that because of the relative nature of this problem? You know what I mean? That this second equation was just like a ghost. Oh, that is really tripping me out. But now we can say that the... Like, why don't I have an equation for the velocity of the... If I know the velocity of the river, why don't I have an equation that I can solve for the velocity of the boat? Like, that boggles my mind right now. Did I set some of these up wrong? Well, let's just throw this number at it. If we have... well, yeah, let's see if it comes out. So if the velocity of the river is 0.833, so let's grab a new sheet of paper. That's what we found out. Velocity of the river is 0.833 meters per second. I have that in my calculator. And that means after 3,600 seconds, this is the speed of the raft. It's just the velocity of the river. We're going to be... So you just multiply these, factor label method, you get meters. And we're going to be at 3,000 meters. The raft's going to be about 3,000 meters after 1 hour, or 3,600 seconds. It has to float for another hour. That's what we were saying. Another hour of time, and cool. So now we need to find out the speed of the boat. Yeah, this way. Why don't I have an equation for the speed of the boat? I don't want this problem to be another, like, 5 hours. Well, we know that the... I don't know what we know. Oh, so yeah, let's just start throwing numbers in. So the simplest thing is just pick a speed of the boat is just 0.9. We can do that again. Meters per second. And, obviously we know the speed of the boat is 0.833 meters per second. And it's because... so the first time is 3,600 seconds, and then the return time is another 3,600 seconds. So if the velocity... Oh, it's because... Oh, there you go. Velocity of the boat is... the velocity of the river plus the velocity of the boat. Actually, yeah, we got that. Oh, why is this problem kicking my butt again? Oh yeah, let's just throw in the actual value. And so we're going to have x plus x. And so now we have a velocity of 1.66 meters per second per 1 hour. And we're going to be at a distance of 6,000 meters. And then on our return trip, our velocities, the velocity of the boat is going to be velocity of the river minus the velocity of the boat actual, and that's going to be 0. Those two things are the same. So we're basically just in place until that raft catches up with us, and at that point we will pass the raft. But yeah. But why wouldn't we be able to solve for this? Yeah, this was really weird. The fact that the velocity of the boat just disappears. So we really don't even have a equation for the velocity of the boat. I'm going to pause the video because I don't want too many more delays. Alright, holy Toledo. This problem is going to haunt my dreams because it was just so bizarre to see that we had an equation with velocity b in it, but then it just poof goes away. And then so I spent my time even just throwing this into my calculator and and then graphing it for the value of velocity b, but you just get 0. Because that's obviously the first thing to come up. But then I was just like, well, but that didn't we come up with that the velocity of the boat is the same as the velocity of the river? Well, then it was just such a bizarre thing. The foreshadow is no, the velocity of the boat can be anything. So that's really fascinating. So what we did is we threw in we got this equation. So in my calculator, I have the velocity of the river. Hell yeah, we did solve for that. That's what we solved for, velocity of the river. And then you throw it into this equation. Well, obviously, this equation has velocity of the boat dropping out. So that means that for this equation to be satisfied, where the length of 6,000 meters with the raft being, the velocity of the raft is this, and then the time frame is that this velocity of the boat can be anything. So we just said, sure, let's have the velocity of the river be the velocity of the boat. Bring that equation, that's 6,000. But we could have the velocity of the boat be 5,000 meters per second, and then throw in that equation. Well, it's going to be 6,000. So that was just real bizarre. That I did not notice that. That I didn't notice that it is based on this continuity. The velocity of the boat is just completely irrelevant, because what's being added downstream is what's being taken away upstream, and it's like the velocity of the boat is just irrelevant to the problem. And that's where I was messing it up with the continuity of saying, well, isn't it just the velocity of the boat that's the only thing that we're going for an hour this way, and then when we go back I was like, don't we just go to like 6,000 meters? Well, no. The problem in relative sense is, who cares about the velocity of the boat? The raft's going to be floating for the raft's going to be floating for 2 hours. And at that point, you're going to be at 600 meters. So that's this, anything. If whatever this time is, you have to double it, because you're going that direction and then coming back. And as long as you're going faster than the speed of the river, you're going to go out for an hour and then back for an hour. So this distance is going to be 1 hour. This distance is going to be 1 hour. And so I have to just chisel this problem into my head so I just don't forget that. And this was the speed of the boat for 1 hour. This was the speed of the boat back for an hour. But this distance right here, this was the raft for 2 hours. So the raft for 2 hours goes 600 meters. Cool. So let's... Man. And so, could we do the problem where we know the velocity of the river? Heck yeah, that's 0.833. And let's just say, what's a really high velocity for the boat? Let's say it's going, not 120 miles per hour. That's like 50 meters per second. But let's say it's clipping along at 25 meters. So the velocity of the boat is 25 meters per second. So, and then the velocity of the river is this. So the relative velocity is the velocity, and this is the velocity of the boat actual. So we're going to be going so x plus 25, and we're going to be doing that for a whole hour. Cool, we're going to go 9,300 meters. Now on the return trip, we're going to be going 25 minus x. And we're going to be doing that for 3,600 seconds. So then the difference between those two numbers is 6,000. Cool. And that took 2 hours, and that was the speed of the river. So the speed of the river times 2. Did I do that right? Speed is meters per second. Oh no. So 2 times 3,600 is this, times the speed of the river. Yeah, that's going to be 6,000 meters. So that's what the boat got. That's what that was what the raft, and in 2 hours, that's where the raft got. But man, so yeah, the equation, that's why they were saying, that's why I get it. I forget the books, but they were like, yeah, you can solve these problems 2 ways. One using relative velocity, one using, the velocity of the boat is going to be the velocity of the river plus the velocity of the boat. But you can just, if you're going Yeah, if you're going faster than the river this way and then slower, I really don't know how. It's kind of a bizarre one, but it's just the same as the raft floating for 2 hours. And so the continuity is if you're going faster than something on a river, where your speed it is the speed of the river plus, your speed kind of in relative sense is the speed of the river plus, your speed on a lake. Your speed on like a lake. I guess this is in a boat. But holy Toledo. Okay, so I think I want to be done with this, and I don't even really know, because it's such a bizarre one, where you just, like, the continuity was everything. I mean, just that aspect. I don't know how you actually figure that out, because we were trying to throw equations, and then it's just interesting how we had to, that took forever to get that relationship from equations. You know what I mean? Just kind of doing the plug and chug, throwing some numbers at it. I'm just going to say some words, but you know what I mean? I'm not going to really say much of anything. So I think we're done with this one. And yeah, if I can make it concise, I'll try. But, at the beginning of the video, I don't know. I might just publish this. We'll see. We'll see. But anyway, thanks for joining me. And guess what? That's a video.